Isso tem que ligar também. Sim, a câmera chuta em você. Okay, good morning. Welcome to the second day of the workshop. Today in the afternoon there will be the handing of the prize for the best PhD thesis in Latin America in classical gravity. So I was just noticing this morning that in only 2 days and a half of workshop, we managed to cover cosmology, gravitational waves, ultramassive black holes, and exoplanets, which are basically 4 of the 5 last Nobel Prizes in physics. So if you are interested for the youngest among you, if you are wanting to pick a line of research, I mean, you have basically the best line of research represented here. And this morning, I'm very happy to have José Diaz from the Federal University of Rio Grande do Norte in Natal, so another Brazilian excellence here, talking about the search for exoplanets with a specific technique he will tell us about. Please.
Thank you, Ricardo. Well, it's a pleasure to be here, of course. I was in the FT when I was a student, I mean, many years ago in the Paulista, so that is new for me, but I mean, some faces are the same. No, Rogério. So today, I come back with discussion with Ricardo. We started discussion in Cambridge a few years ago when Ricardo was in the LIGO community. We tried to discuss this connection between stellar evolution and big problems in cosmology. So that makes sense because now I have many nice observations. So one of these observations is this photometry that we did that for thousands, millions of stars at the same time. So I put here some, let's say, some fundamental stuff about exoplanets, but my focus will be microlensing, exoplanets for microlensing. So this is new, it's exotic at the same time, and I think you will figure out that microlensing is probably the best way to know the connection between star and planets. So we have one, we can see one solar system, but when you compare this solar system with other solar systems around the galaxy, we can see that the architecture, the structure of this solar system is not usual. It's really hard. You have no answer for that. So talking about the solar system, I like to start it with this plot. With this very, very easy high school plot. Oh, sorry, the laser point. Just to, is this one right?
Yeah, the pointer is the top one.
Okay, thank you. So when you look at the solar system, our solar system, we have small planets in the left. The Earth is here, of course, and we have these 2 big planets in the center of the solar system. You have another big ones, these kind of big balls from gas and with some helium and hydrogen. So it's really strange that the big planets in the solar system fit inside the middle range of the solar system. So without other example, we accepted that, but it's not easy to figure out from the theoretical point of view. So that is one of the questions that's coming from this problem is the stellar, how stellar burning, how planet is formed, how connected is star with the planet. So it's not an easy thing when you figure out that is a turbulent way to do things. Magnetic fields is there. We have all the connection between small process, large scale, time. So that is one of the complications. But the physics is really, really close to explain what things drive our solar system. Here's a plot that shows the sun, the Earth position, this asteroid belt, and the Jupiter. So we can see that large particles probably form in dynamical process all the protoplanets that you can see in the solar system, like the proto-Venus, proto-Earth, and Mars. And this part of small particles did form the big planets in the solar system. That is a paper, it's quite a classic paper in the field. And this kind of process, it's more or less accepted for the Earth-like planets and the gaseous, the Jupiter-like planets. From the observational side, we have this very nice ALMA image That is from VHA tau. It's a Orion region object. So you can see the star. You can see the disks. You can see some gaps in the disk that are the position where the planet were formed. So you have no matter because the matter is in the planet. So that is really exciting kind of image. And the simulation of this stuff was did before. So that is one of these cases that the observation meet the observation. I mean, the theory meet the observation, and the observation comes after the theory. So grosso modo, I mean, in large sense, we can see that the process from A to E is a kind of time. When the time passes through, we have the formation of the solar system. And in these small planets and the big planets, and it's more or less divided by this fixed line. That is the snow line or ice line. That is the division between planets that are too hot and planets that are too cold. So this ice line is important because life depends on water. And in some sense, water, it's kind of fundamental liquid to start life. In comparing what this paper from Science Advances show is that these small planets is completely adapted to our solar system view. You have these small planets, and the small planets are here. We have the ice line, and you have the big planets. And this ice line is important, and I stress here because with microlensing, I will discuss exactly about small planet in this zone. That is not easy from the other techniques. So, again, rock planets, the snow line, the gas giants. So, I mean, until 2019, until 1995, that was the big picture. The physics of the star formation was quite good to explain the rock planets, the snow line, these asteroids, like you have some very low asteroids that fits in this position, and these gas giants. And I will pass through slide. I don't need this today. But in 1995, Michel Mayor Didier Queloz published the first exoplanet around a solar-like star. That was 51 Pegasus B, that was around the 51 Peg. 51 Peg B was a Jupiter, a hot Jupiter, hot because it's too close to the star, and a giant Jupiter, kind of 0.6 Jupiter mass, and close to the star, short rotational period. If you compare this with our solar system, we have a problem. Because it was good, I mean, it was quite good, the connection between the planet formation theory and our solar system. But now we have another star with a Jupiter planet close to the star. So that was a kind of, I'd say, I mean, Michel Mayor Didier Queloz got the Nobel Prize for several reasons, but that was one of the reasons because the field coming very, very, I mean, hot, exciting. I have two pictures here just to, Ricardo mentioned the Nobel Prize. Here's Michel Mayor, that is my thesis advisor, and that is students that are connected with Geneva in the 90s. And here is Michel Mayor taking this professor title from Natal, from my home university. That it was before the Nobel Prize. That is just funny to see these plots. By the way, forming stars is a hard problem because we have to put now migration. The Michel Mayor Didier Queloz point was Jupiter, as close as the stars, need explanation. One explanation was that probably the planets could be migrate from the far away to close to the star. The second point is that we can need to figure out the influence of the stars, the dynamic interaction, the tides, the disk properties, all this stuff together with stability, magnetic field connected to stability. That is, I mean, theoreticians know that that is not easy when you put these things together. And to test these theories, we can use now the exoplanets. The question is that when you look into the exoplanet, or for these many exoplanets that was discovered, we need to figure out if you can compare the physical process during the star formation with the exoplanet that is seen now. what is the connection between the early time of the formation and the distribution that we can found now. So, and that is one of the problems. For example, we have some planets that figure out that are in some desert. When you put mass along the eccentricity, for example, we have some region that there is no planet. And other regions has too many planets. So figure out this desert is a kind of test to the theory of stellar formation, of the planet formation, sorry. The paucity, I mean, we have no planet giant around low mass stars. That is another problem. How figure out that from the theory? And some planets that are, we call that free floating planets. Planets without stars. Strange, but there are some. So that is just to give you some ideas that it's connected with a statistical view of planets in the galaxy. We need to do some, in some sense, a kind of demographic study of exoplanet. And for this, we cannot study star by star. And again, microlensing is important for that, because you can access thousands of stars at the same time. So, in other words, the proposition is really easy. So, study the diversity of planets, do some histograms, and see how the things are, I mean, in the physics connected with the theory. That is the easy things. To find exoplanets, we have more or less 5 tools only. We have radial velocity, that was the technique used in the Nobel Prize planet. Transit, radial velocity, direct imaging, gravitational microlensing, astrometry. I will pass through this very fast. I don't care about all this stuff. Of course, I will talk about microlensing. But it's nice to see how things are. I mean, radial velocity is very easy. It's just a spectroscope techniques. When the planet go around the star has just some movements around the center of mass. And that could be, measured by high-resolution spectroscopy. That is the radial velocity techniques. The transit is the technique from the Kepler, the Corot satellite, the TESS now. That is, we can measure the light. I mean, we have a photometry, a very, very good photometry that can detect it when the star passes through the stellar disk. You can measure 2 points and take the orbital period. The other techniques is the direct imaging. That is nice too, because you can take the star, here's the star, we can put something eclipsing the star and take a measure of the planet just close to the star. But that is not easy for a star. I mean, the planet needs to be very, very far from the star to these techniques. There's only 1 or 2 planets are inside these techniques. Astrometry, that is important because Gaia is there. Gaia is the new satellite from ESA, and we can measure the position of stars with a very, very good precision. So if you have this precision for all the stars, some star that has some movement is because planet is there. So that is quite new, I can say, techniques, and that is possibly for the future one of the techniques that will give us many, many exoplanets. And finally, the gravitational microlensing. So the gravitational microlensing, it's completely based on general relativity stuff. And we can measure some positions, some stars, and figure out the interference of the mass in the background stars when a secondary star passes through the background stars. So the light of these stars is here, and when these 2 stars are in front of the field of view, we have this magnification. And if the target star has a planet, you have a perturbation on this magnification. I will show a little bit more about that. Just to mention these techniques and my team in Natal, last Friday, we just published one exoplanet that was almost completely composed by water. This exoplanet is the connection between 2 techniques, radial velocity and photometry with TESS. So now we can use 2 satellites, so 2 observations, 2 messengers, 2 kind of light, to study the same planet. So that is some releases from the last week, just to show you some.
Question.
Yeah, sure.
How do you know it's mainly covered by water?
Well, that is a very good question. Let's answer because it's an exciting question. When you take the radius of the star and the mass, possibly for planets observed from photometry and spectroscopy, we can solve the mass and the radius. And you can write the state equation, like, a state equation for a planet. And you have this diagram that you can put the star in the position that is iron, because if it's too heavy and too small, it's an iron composition. If it's too light and too big, it's a gas, it's kind of liquid or gas combination. And for the star, the position of the star in this, PV, this is state diagrams give us a water world, kind of mainly composed by water. This is one case because we have many observations from this target. We have photometry, infrared photometry, so we connected all the possibilities that we can do for one planet with the star. By the way, our problem is not only the easy cases. The question is that to find planets like the Earth, around the star like the Sun, we have this kind of problem. The Earth has this size and the Sun this size. When you compare the activity of the Sun, all this, the dynamical of the star, the Sun life, these affected the measurement of the radial velocity. I can do the same study about about the limitation of each techniques in compare with microlensing, but that is not the sense here. I will not do the same kind of connection, but for radial velocity I will do, because the Sun is a magnetic star, and the radial velocity is a measurement from spectroscopy. In spectroscopy, when something moves in the surface of the star, in the atmosphere of the star, the spectroscopy has this movement. So if you want, if the focus, the objective, the goal is to catch up a small planet, you need to figure out all the activity of the star, like magnetic cycles, spots, all these things that change in the stellar atmosphere. By the way, so with this, I can probably give you a point. Microlensing is probably the only measurement that you don't care about the star. You have the question, you have the effect, we have the measurements, and we don't care about the star. So a microlens exoplanet is a kind of planet orbiting stars. And these stars has a background stars and all the stars that pass between us and the background star. And when this happens, we have this combination between the light of the background stars, the lens for the second stars, and a possible planet or a binary or another object, another third body or a second body that they're forming the image. So that is a very easy thing. And it's based more or less in the relativity. You know that before the general relativity, Einstein writes some hints about the detection of the star behind the sun. And Einstein say, well, I expected a 0.84 arcseconds of the deviation of the star. Here's the cartoon. The lens, the sun is here. So this inclination is more or less 0.845. After Sobral, Rogério was there, and Ricardo too. We see that many times. So we have here after the eclipse in Sobral and Island Primes. So you got the true value by using the general relativity. And the effect is possible, and you can measure that. So the point is just looking the star that we call the lens, the source star from an observatory, we can measure the distance between the true image and the lens, the format image. And the more straight, oh, sorry. I lost my mouse here. Okay. So, if you put this idea, just classical equations, like we can measure the distance between the real image and the secondary image, that is just the deformation from the general relativity. We can find the alpha, I mean the distances between the three images, the secondary images. And we can compute this radius. Of course, it's proportional to the mass, and over the, it's proportional to the mass, and of course depends on the Schwarzschild radius. So just writing this equation to fit in a distance and to put the Schwarzschild radius and the distance below, we can write this equation here that we call the Einstein angle. That comes from the radius, the Einstein radius. And that is not, this equation, Schwarzschild radius over the distance, is not far from the original equation published in 1936 by Einstein. That is the beta here. So Schwarzschild radius divided by the distance. And Einstein say, of course, there is no hoping of observing this phenomenon directly. Einstein was, well, some people say that probably that was the only time that Einstein was not correct. I'm not completely agree, because we know now that we need to observe 1,000 of stars, probably 10,000, 100, millions of stars to get one microlensing. So if you think about 1936, it's probably a statistical view that there's no hope. And by the way, I will pass through some equation again to show that we can do that for one lens to two lenses for many lenses. That is the same process. Of course, to do that, we need a little bit more of geometry just to write things and figure out how all these lenses is connected. But that is not, we stay in this very traditional way to do physics. And we have here the lens, the Einstein angle. Each of these rays will produce this magnification. That is a very simple problem. And with this, we can expect this kind of situation. The magnification of a single lens without nothing. A background star, a secondary star, an eclipse, just magnification. The second case is if planets exist. You have these two kind of corners. You have these two peaks here. That is a single problem with two planets. We have another thing that is how to verify that is a planet. That is like the field of view is drive between the geometry, because you have the background stars, you have the secondary stars, we are here, but the field of view could not be in the same line. So we have many possibilities that need to be figured out, and we call these possibilities, that is probably the most difficult thing to do with this stuff. We need to compose all the solutions at the same time. So let's go to a more observational. I have 10 minutes more. That's perfect. So that is one of the cases. I'll go to 2012, 2013, BLG 0371. That is one star that one day start to be magnified. And the people say, oh, let's go observe it. The difference between this point and this point is months. It's 2 months or 3 months. So we observe it every day. You can see the magnification only because two stars is one in front of the other. So that was one of the first time that we compare. The OGO was a survey. You did the observation, we did the model, you started to figure out how to do these things. I will not talk about caustics, but just to give you this idea that the caustic is very important, because The caustic is here, have a very, very nice caustic here. The deformation of the lens when the light passes through, and if the lens is not perfect, the focus could not be a point, but you have this region of the focus. This is this envelope of the light. You can see the same thing when we study micro lenses or lenses. For the exoplanet, for example, we have the caustic associated to the system. I mean, we can figure out the magnification, but you can also talk about the caustics of the stars. And I will not give you, I can discuss this solution after. That is a solution, that's a more general problem, is a generalization of the problem. We have all the solutions. We can write a polynomial solutions that is the same way we do for many problems in physics. And we can now do a model for one star in the background, one star between the star and the observer, the pass-through, and the planet. And here, exactly we expected. A magnification, a secondary peak that is the signature of the planet. This question was studied in some cases. For the synthetic case, we can write the caustic. That is the caustic. Go ahead.
So how come the magnification of the planet is so strong? I mean,
The magnification has, the planet has no magnification because the planet has no light. The magnification is the effect from the light of the star and the second one.
I understand, but so how come is it as strong as the one from the star?
Depend the star.
I'm thinking it depends on the compaction. The planet's compaction is much weaker than that of the star.
Yeah, sure, but the point here is how massive is the star? If the front star is bigger or is dense, the lens is strong, and the magnification is more strong than a more, teeny star. So the magnification is only connected to the star mass.
No, that's precisely my question. If I see the second bump,
Okay.
So if the second bump is associated to the planet, how come the second bump is as similarly comparable to the first bump, which would be the star?
In this simulation, we simulated two planets, not only one. So the secondary, because we pass through, you have these two bumps, is because the geometry of the system changed. In this system, we have two planets. It's just the next slide. That is the system that we try to figure out.
Since we interrupted already. So is it correct to say that the main parameter that tells you what is the height of the magnification is the compactness of the object, m over r of the lens?
Yeah, we'll call this the key. The connection between the two masses that give the luminosity, the magnitude of the first and the second. And the planet, how close or how far the planet is, will give the time scale of the observation. For two planets, that is hours or 1 week, this bump. And from here to here, you have many weeks or many months. Because, a small planet is just turn around very fast. So here you have a planet, and you have these two surveys connected. That is important to mention because it's the first planet detected. And that is from Ogo. Here's a more delicate process. In this case, you have 1, 2, 3, 4, 5 planets in this event. So you can see the caustic is not easy too, by the way. So that is one good example. It's called classical example of microlensing. I will finish talking about this Earth 2.0 because it's a very small planet, and we observed this along the COVID. We observed this in 2020, 2021. And that is more or less the work of my former student, Leandro Almeida. He is the man behind many of these plots. And for many of these observations is from Leandro, we call TED. And that is the planet. You can figure out that it's an Earth mass planet in the time of COVID. We observed this, and we did the model for the magnification. That is the magnification. you can figure out, we can see here the name of all the observatories that was observing this campaign. And more or less the observational strategy is, in Australia or in China, an astronomer started to see a magnification of the star. He calls some friends in CTIO in Brazil and Hawaii. I have a problem. One star started to be more stronger. Can you observe it? Yes, I have time. So that is the way to do these things. Of course, it's not easy because sometimes we are in the observatory, sometimes not. Here is the Leandro observing in Brazil, in OPD. And for this observation, a very nice result is that when you connected the Q is the reason between the mass of the planet and the mass of the star with the same major axis, we can see that our star is this one. So it's actually the more close star to the sun in terms of mass in orbital period. And here's these tracks are the points that was put in 2016, 2019. So that is a very, very nice result because it was done in the COVID. What robotic observation was not easy as observation, and we did. Here's one big part of the observatory that you use, some in Australia, South Africa, France. EOPD is a very nice observatory to do that because it's a small telescope. You can do that very fast. You can just go there and observe. Let's move a little bit more fast. I don't talk about strategy today.
You have 15 more minutes. You don't have to hurry.
Yeah, I have.
Yeah, you can go on until
okay.
10:50.
Yeah, so it's 50 minutes in the whole presentation. Good.
Yes.
So I come back to strategies just to.
Yeah, take your time.
Okay.
Anyway,
this
I'm
is
sure
good.
there will be a lot of questions. So.
Good. So the strategy to do this kind of observation is not easy because we are only in our house with our family, and at some time we got a mail, just, hey, José, I have a high magnification event that is currently undergoing an anomaly. That is, the nature of the anomaly is currently unknown. The event itself is very bright. Ricardo, you asking, 12. 12 means it's coming to here. The magnification is exactly how the light curve started to be, enhanced. And attach the figure from which Zhang, and it then find the anomaly. So the current data is from our LCO, that is the survey. That is seen by Jennifer, that is my collaborator in CFA in Harvard. So, and we got this email, and sometimes we have time in the observatory, sometimes we just lost the planet because we have no time. And if the magnification is exactly inside, just coming to this, if the magnification wrapping to solve the planet is in a period that you have no time, we lost the planet. So we need to solve the timing when the planet go around and the second peak is there. So it's easy to imagine that finally with microlensing and the actual way to do that, we lost most of the planets. So it's really hard to get a planet because the strategy is not easy. So now we have this strategy. So that is one of the fields that we use. Here is all the fields separated. And for few of these stars, every year we have this follow-up of these stars. And we can, in fact, put this in observations. And times we have this kind of email or Twitter. People use everything today to join the scientists to go to the observatory. And in this way, I can say that the planet that we discover with microlensing is far away, the more exciting, because are exactly in the ice region, exactly the region that we are looking for. Answer a question as how frequently you have this kind of Earth planet with water. And looking from some exoplanets revelated by microlensing, here you have the mass of the planet, and the same major axis. So that is a plot from 2017. Red for transits, green for radial velocity, pink for imagings, astrometrics, and microlensing is this purple. The Earth symbol is this one. So we can see that by 2017, 3,600 planets was discovered. In the situation of the Earth, 0, no planets. That is not only the planet for microlenses, all the planets discovered until 2017. That is what this plot means. For sure, these points here are big planets in short periods, right? These planets here are small planets with short periods. And the blue here are more or less like the Earth orbital periods, but big ones. That is the hot Jupiter, like the first one from Michel Mayor and Didier Queloz. It's a hot Jupiter. It's a Jupiter close to the star, spinning, in a very, very fast spin around. And finally, if you go to 2021, it's not, it's not a big change of the picture. For sure, we have some more nice planet around the Earth, and all these planets are purple. That's mean microlensing, okay? So looking for microlensing planets, that is the focus in microlensing. We have all these planets from big planets with the same major like the Earth, until these planets that are around. And finally, sorry, yeah, go ahead.
So what's the underlying reason for your selection biases? You don't like small or large semi-major axes. They have no problem in masses, but you do seem to have an issue in the semi-major axis.
We have the same plots with many axes. We can do that with masses in same issues or masses with the H. The issues you talk about, it's not. I don't see why this is a problem.
No, I'm not saying it's a problem. So, but you mentioned, oh, look, none of the techniques seems to be homing in on the Earth. But of course, all of the techniques have their own selection biases. Yeah. So are these methods intrinsically having some particular bias that would prevent us from seeing an Earth mass? And then why do I care if I don't see an Earth mass?
Do you remember I mentioned the magnetism of the sun? That is one of the bias. The noise from the star is one of the bias that keep the radial velocity limited by some bias. So that is wow, that I don't hesitate to come back because your question is really important to be not mentioned like that. That is mass again, and the publication data. So 1995, the first one, 50 unpack. And radial velocity started to take many planets. And here's the threshold of 1 Earth mass. So we can see that the bias exists. So it would be not possible with this technique to come into the Earth mass planet. Of course, some groups say, no, we have these extreme stability instruments that can go beyond this level of noise, but it's not easy because the noise is not from the instrument. The noise is from the star. So we cannot, so that is one of the limitations that we can talk about. And by the way, the instrument that we used in this publication that I mentioned was a Spiro. Spiro is a spectral polarimeter in the infrared. So we can go with the infrared around this line because with the infrared, the stars seem to be more quiet. And that is one reason that to use infrared is not visible to go beyond this threshold. By the way, let's come back to our, okay. So yeah, microlensing give us these planets. In 2001, well, not bad. If you compare 2017 from 2021, The comparison between these two periods is because my student did the thesis exactly in this range. So that was exactly the defense slides showing these two. But yeah, I can summarize in terms of mass over some major axis, all the stars that we know by 2021, the star that we discover, I mean, the planet that we participate in the discovery, that was this very, very close to the Earth mass, and in the background, all this one is also associated to our theme. So that are new exoplanets with the UFRN, the Universidade Federal do Rio Grande do Norte, connected to the paper. And, well, that is more or less in terms of, let's say, publicity or selling something. I can give you the idea that microlensing is really, really an important technique to go far in this field. And we have many issues from the theoretical point of view. I can discuss this in the questions.
Can I ask you something?
Yeah, sure.
Why it's favoring one astronomical unit as the distance, typical distance where you find of the planet when you find microlensing? It looks like it's centered in one astronomical unit. Yeah.
Remember, there's no line. The ice line is this line. It's more or less this line. I mean, here is probably too hot. Left side for you is too hot, right side is too cold. That is more or less connected. There's no line. I mean, the Earth is here, so there's no line. Is a little bit not far away from here. But then
you could have icy giants or something.
So yeah, so that is why this line is, for us, is a kind of important line. Okay?
If I can follow up on this naively, I would expect the planets detected via microlensing to follow on a line of constant slope. I mean, basically increasing mass and increasing radius.
That is true.
Fixed mass over radius.
That is true.
But no, they seem to be vertical.
I mean, you talk about this envelope here, right? It's not. It's not.
I was expected to follow around this line rather than vertical.
Yeah. Well, yeah. The bias that you ask about. One of the bias of the microlensing is the time that we can follow up the event. So we cannot follow up for 6 months, so you have some constraint in this same major axis too, okay? So just putting in a time, it's important probably talk about this 989 because one astrophysicist from Harvard, from CFA, and in the 18th, another one in the 18th from US, published some strange exoplanets around pulsar and around other objects that was not accepted by the community as a real planet. So now we know that in 1989, we have this pulsar planet. In 2019, in the 90s too, we have another planet that was activity, was not real planet. And that was a scientist from the CFA. And we have, in 1995, the natural occurrence, I mean the natural frequency of the planets from all the techniques, and the situation is, today is more or less here. I did this plot just before taking the flight in the Sunday. Okay, that is just an updated situation, these two. I mean, you can, now you have the eyes to look at for all parts of this plot. Again, you have more or less from here, the ice line, and you have these two hot and here two cool planets. Okay, Ricardo, you talk about the aspect of these plots. I can give you another idea is that, for example, Kepler is a nice machine to discover planet. It's only associated with these volts too hot. And we need an instrument to do same thing like Kepler in the right side of this plot. The instrument is accepted, more or less, is the WFIRST, or the Nancy Roman Space Telescope. That is probably the next big instrument to do that, because it's a really wide field camera. So that is the field of the WFIRST, or Nancy Roman. That is the Hubble field. It's a kid game with this kind of machine because we have millions of stars at the same time, the photometry of all this stuff in the real time, okay? So we need computation for that, and we know that. That is why my student and myself, we started to figure out how to be more efficient, more focused in the search for solution. That was one of the papers from the Leandro thesis, and it was a process to search more, focused on solution. That was published in an astronomical journal, and it's kind of Python simulation. We search for all the solutions, and in this search for, we can search planets that are too far, too close, too big, and you can see here, each peak of that is one possibility in the geometry of the planet, the background in the star in the background, the second star in the planet. So we did this paper exactly to the next WFIRST and Euclid's mission, because that is the kind of science that we think will be relevant, will be strong in the next years, the next decades probably. So I will come in from my last slide. So that is, again, that is the same paper, just to be more focused on how to search this region of interest in the simulation. And, well, I would like to give you some hints here. Microlensing is important. That is one thing that, my message is that. And probably we can access small planets and the ice line. That is one important thing to say here. It's more sensitive. That is true. We can go to planets far away in the galaxy. We can go to the planets in all the galaxies too. So that is awesome. And the only method also that we can, connected many things at the same time for the density of planets, for the statistics, for looking for how common one planet or another one is in the galaxy. It's capable of detecting with some probability multiple planets. That is possible too. Also, in summary, microlensing can be used to study the statistical abundance of the exoplanets in our galaxy. And we can do this sense. That was what I expected in my first slide. So I say that microlensing can do that. So thank you. Questions, please.
Thank you very much. I enjoyed a lot of your talk. My question is a little bit in like the one that Luis asked. So you mentioned that the fact that it's measurable is the magnification, right? That gravitational potential from the planets effect on the path of light, right? But I don't think I understand very well how you need to model the caustics in order to take into account this effect. Because, wouldn't that just be a question of let's wait for the potential to, the gravitational potential on the plane that you're observing, the potential of the planet being added to the star one, and then you just have a single magnification event? Why do you have to model the caustics in order to take into account this magnification? I don't think I understand it very well.
Probably the best way to answer your question is think about the simulation. How simulated this? We started to put together a background of photons, okay? That is photons that's coming from the background star. Second point, we take a secondary element, secondary mass, you pass through this background of photons. When the first light passes through the potential, we have one lens. When the second ray passes through, we have the second element of the lens. We call that second lens because it's connected to main lens. So the time goes through, and you have this combination, and the images coming in this different way. So that is one planet, sorry, one star in the background and one star in the front, okay? Let's do the second simulation. Same one, but you put a secondary component. A planet or a binary, a broad dwarf, whatever. We have the first, the star coming, the first light coming too. We have the caustic, we have the formation of the star mass, the forming the light, but the planet has a dynamic timing that is different from the timing of the star coming through. So all these things is connected with the magnification. So that is, magnification could be really more complex than one peak or two peaks. It could be negative, it could be really in a big...
Yeah, because it's not something that's just a point being added to the potential,
yeah,
right?
Yeah, but my point now is, once simulated all these phases, you can change the place where you are to look at this event. This could be completely aligned, this could be like that, this could be, you know. So the image format is the combination between the background, the star, and the observer. So in the simulation, we can play with this. In the caustic, it's one kind of, how can you say, manner to see the same thing. Not the same thing, but you know, it's associated with the caustic, like in a glass. When the sun coming, the caustic we change at the same time. So the caustic is the final combination between everything in this phenomenon.
Okay.
Yeah.
Thank you.
So it's a very naive question. So you have the lensing effect on the background star. So the question is, do you see the star that's in the front, or just see the magnification of the star in the back?
Yeah, we have just the magnification. The magnification is between the background star. You have the magnitude is constant. You have no magnification. The star alone is there. One day, this star started to be magnified. And we can, if you search it for something, you can see the second star that's coming close.
So you can see the second star.
You can see the second star.
Okay.
And you can, well, depends of the star. Some
Right.
star is not possible, of course. But yeah, in some sense, we can see, you can observe the star if you figure out which star is hard. It's not frequently,
Yes.
but it's probably a nice thing to do. I don't know if we did that for one star precisely, but we know that one star coming, and we can observe the secondary star, the two stars at the same time, and probably follow up a little bit more the secondary one.
Yeah,
Depends of the brightness.
Yeah. So the reason I ask is because this microlensing technique was also used to search for dark matter in terms of the macroscopic dark matter. So if you don't see the star, you don't know if it's a star. So it could be interesting.
Yeah, I discussed with Thaisa before my talk that I guess that the guys from dark matter was the root case of this exoplanet, because all these guys looked for something wrapping in these stars, and he figured out, wow, probably a planet is possible, and that was a little bit, the way was corrected to do planets. So the same of W first. We talk about galaxies. Nobody talk about microlenses from exoplanet. A student from Natal is trying to figure out how possible will be W first for microlenses. We don't know, because it's a really wide camera, but yeah, who knows?
Okay, thank you for the nice presentation. I have a curious question about the planet which has water. What are your thoughts? Can it support life?
Sorry, could you?
Can the planet which has water, the one that you observed, a curious question, can it support life? I don't know.
Yeah, absolutely. The main point is life. Well, people discuss a lot about life now. So if life is possible in one planet, in another planet, I personally say that life is possible in many places in the universe. The moons, it's probably a good place to life be there. But planets in this ice zone, it's the main target to search for life. And the other NASA missions, like now WFIRST, for example, is we try to do this transmission spectroscopy. It's, in some senses, it's close to this process. We have one star, and the planet is around this star. And when the planet goes through, we can take the photon, we can observe the photon that go through the atmosphere and know if the atmosphere has some water. CO2 was discovered 2 weeks ago, I guess, in one exoplanet. That was exactly the techniques that could be relevant to search for life. And if the planet has water, it's more nice because life needs water to start it. Big proteins, you know, big chains. That is one thing important to life.
You have a question?
So yeah, so this is also a very naive question, following Rogerio's. So everything here you're doing in the optical. So can you do microlensing with our frequency? In particular, I'm thinking, given what you mentioned, all the structure and activity of the sun that mess up with your noise level. Yeah. So if I now look for a coherent source of radiation, say I'm thinking pulsar on the radius, of course I had to be lucky for something to go through, but we have been following pulsars for decades through nanograv and the PTA. Is there a chance to do it with radio?
Yeah, well, that is not a naive question, my friend. It's infrared. I mean, it's not easy for me to know how to adapt the lens in the optical to the infrared. My naive answer is yes. I think the lens, all the physics will be the same. Is we just change some lambda to the left. We try to see, yeah, lens in the near infrared or in the red. And things like pulsar, it's not easy to observe it, what's go on close. But yeah, I think with the next NASA observatory, I guess, is Louvois. You'll be observatory in 3 channels: visible light, red, and UV at the same time. So probably with this kind of machine, we can start to figure out, you know, what's happening in the visual light at the same time in the red, in the blue. But I don't know. I don't know about the lenses in the other lights. Yeah, frankly.
There are no further questions. I have one question, so I take advantage of my question. Sorry, you're putting the ice belt around 1 astronomical unit, but that's assuming that the star is sun-like. I mean, isn't there more variation of stars?
Yes, that is one part of the problem. Of course, like, yeah, assuming that the star like the sun, could have planets like the Earth, we search for this combination of the star. But that is an assumption to start with something. Okay. And yeah, but it's like you found a friend, a brother that you lost. We started looking by people that is close to you, right? So that is the same process. So yeah, this
working assumption.
Yeah, is one assumption. But of course, the moons probably could be a good. I mean, moons close the star. It's probably one good place to be there. Yeah.
Okay, one last call for question. If not, let's thank José. Okay, while Thaisa sets up a laptop, I have 2 announcements. So first, don't leave after Thaisa's talk because we're taking the group picture, the conference picture, right here outside. And second announcement is that we have the list of the people who are entitled to free food tonight. So please come in after the talk and mark your name. Otherwise, you won't get free food tonight. Okay. And by By the way, is free food and one unalcoholic free drinks, and then if you get alcohol, then you pay on your own. That's the rule of ICTP. I'll represent the speaker. So now we move from the north of Brazil, a few thousand kilometers south, to the other tip of Brazil, to Rio Grande do Sul. And also we move from small planets, from planets to supermassive black holes. So it's even bigger jump, but it's equally fascinating. Thaisa, please.
Thank you. Okay. So I thank you, Ricardo, for the invitation to talk about my work on supermassive black holes. So what I'm going to talk about is how I observe supermassive black holes. And the summary is, for completeness, explain what is a black hole, again, maybe you know, and which is our location as humans, the humanity in the universe, and the black holes, where they are. What's the connection with us? And why supermassive black holes matter. Okay? Then I'm going to talk about my work on my team on the feeding of supermassive black holes. En passant, I'll talk about the event horizon observations of M87 and Sagittarius I stars, which is the black hole of the Milky Ways, call it Sagittarius A star. And then I'm going to talk also of my work on feedback of supermassive black holes. And finally, a little bit of our project. We have an approved project to observe supermassive black holes in active galaxies with the James Webb Space Telescope. Okay, so just for completeness, let's remind ourselves what is a black hole. So black hole is just a consequence of gravity. So if you have this old Newton equation with the force, gravitational force, if you increase the mass of an object, you increase its gravity, but you also increase the gravity if you decrease the radius. So what will happen if you keep increasing the mass and decreasing the radius, where it will go to the limit, which is the black hole, where in a black hole the escape velocity is the velocity of light, so not even light can escape from this imaginary surface, which is the surface with the Schwarzschild radius. Okay? And this guess of the presence of black holes or black stars was made already back in the 1700s by John Mitchell and Laplace. In the Einsteinian view of gravity, so the masses in the universe warp the space-time around it, and then you have any object that enters the gravitational field of a black hole will follow a curved path, but not only objects, not only bodies, but also the light radiation will follow a curved path due to the warping of the space-time. So we have the space-time curvature given by the Einstein field equations. So the stress and energy tensor will dictate how the space-time curves. Okay, so we have objects with different gravity, and the sun, for example, distorts a little bit the fabric of space-time. If you have a white dwarf that has the mass of the sun, but the radius, much smaller radius, you have a deeper warp, and then you have a neutron star, even deeper warp. deeper warp. And then the limit is, you know, when you have a black hole with infinite curvature, and then you have a singularity, all the mass is in the singularity inside the black hole. One property of the black holes that we use always is the radius of the event horizon that was derived by Karl Schwarzschild, solving the Einstein equations, and this is the radius from where nothing can escape, not even light. Okay, so we see that the radius is only proportional to the mass. So, and for example, for the Earth to become a black hole, we have to compress it to 9 millimeter radius. Okay, the Sun to 3 kilometers, and the Sun has 700,000 kilometers of radius. In the Milky Way, we have a supermassive black hole in the center that has 4 million solar masses, and then it is Schwarzschild radius is 12 million kilometers. Kilometers, not kiloparsec. Okay. Well, a little bit of perspective now. So we live in a galaxy, the Milky Way. This is an actual image of the Milky Way in the sky, but we are inside it, so we see it from inside. This is the center of the Milky Way. So we are 27,000 light years from the center. And the Milky Way is a spiral galaxy that has a bulge and a disk with spiral arms. And we see the universe and the galaxy from inside. Two important structures that, of galaxies are the bulge. This is Andromeda galaxy, only 2 million light years away. And another thing that is important to remember is that the universe is so big that and the velocity of light is finite. So we look at Milky Way as it was 2 million years ago. M87 is another type of galaxy, an elliptical galaxy, which is 53 million light years away, and has only bulge. Okay, so Andromeda has bulge and disk, M87 only bulge. Well, so when we extrapolate observing the universe farther and farther away, we can observe the whole history of the universe. So this is, maybe you know already this, this figure from WMAP that shows that we are in a universe with 13.7 billion years. And when we look far, we are looking to the past of the universe. And we are reaching now, we have reached already we can see the microwave background radiation. And with James Webb Space Telescope, we are aiming to see when the dark ages finish, when the first stars in the first galaxies form. Okay? So we know that's more or less in a few 100 million years, but maybe we can go down to 50 million years with JWST. So this is one of the main goals of the JWST, to find the end of the dark ages. Okay. We have, this is the Hubble Ultra Deep Field that maybe you already have seen. So from the Hubble Ultra Deep Field, we know now that the universe has more than 20 billion galaxies in the visible universe. Okay? At least in the universe that we see, there are at least 20 billion galaxies. And in each one of them, there is a supermassive black hole in the center. Okay? So we know that all galaxies that have a bulge, actually there is a requirement. The galaxy has to have a bulge. When the galaxy has a bulge, it has a supermassive black hole. Okay? So just quickly, I will not enter into detail here, but this is like a supermassive black hole simulation with an accretion disk, and you have all the gravitational effect of gravitational lensing, showing the accretion disk around it and the back part of the accretion disk, the top part of the back, making this part of the ring, and the under of the accretion disk, the bottom part of this ring. Okay. And besides, each galaxy with a bulge has a supermassive black hole in the center. They have an estimated 100 million stellar black holes in the galaxy. Okay? This is the end result of the evolution of massive stars that explode as supernovae, and then you have a black hole resulting from this explosion, and these stellar black holes are usually more easily found in binary systems when it has a bright companion and it captures mass from this companion in the accretion disk. Okay. One important property that we know already from Hubble observations is that the mass of the supermassive black hole inside in the nucleus of galaxies is proportional to the mass of the bulge. So bigger bulges have bigger black holes. And we also know that, so besides being ubiquitous in bulges, I just showed you that its mass is proportional to the mass of the bulge. But then we have also, we know already from studies of the distant universe, that the mass accretion rate density, which is this red line, follows the star formation rate density over the history of the universe. So they seem to evolve together, the supermassive black hole and the host galaxies. And they evolve together, and also there is, I would like to show you that the black hole, supermassive black hole, produces feedback that in the form of radiation and jets from the accretion disk that affects the galaxy where it is inside. Okay? But how to observe these black holes? Okay? I have observed mostly, and most observations are via electromagnetic radiation, but one can ask how you can observe black holes with electromagnetic radiation if they don't emit light. So actually we observe objects that radiate, that send the electromagnetic radiation, that orbit the black hole. Okay? And also via the same process that José was talking before, gravitational lensing. And there are some results of black holes passing in front of stars, and we see the effect, the variation caused by the gravitational lensing, amplifying the light of stars when it passes in front of it. Okay? And also, you already know also that since 2015, we began to detect gravitational waves from mergers of black holes or neutron stars with black holes, and with these detectors LIGO, Virgo, and CAGRA. In the future, we hope to detect not only stellar, because we have detected only stellar black holes now, the merge of only stellar black holes, with these gravitational wave detectors. In the future, we have this project of the LISA, which is an interferometer similar to LIGO, but that will go into space. Okay. To talk about my work, I would like to begin talking about quasars. Okay? So quasars can be considered one of the first evidences of the existence of supermassive black hole. So quasars can be considered the most luminous objects in the universe, and they were discovered as radio sources. When the distances of them were discovered, it was found that the luminosities were almost 1,000 times, could reach 1,000 times the luminosity of the Milky Way, the whole galaxy. Okay? And then, since the Hubble went to space, we now see that quasars are actually the center of galaxies. So quasars are not another entity, but it is in the center of galaxy. Okay. But how we can explain that in the center of a galaxy you have such high luminosity that can outshine by 1,000 times the light of the galaxy? So the explanation is that in quasars we have a supermassive black hole capturing mass. Okay? So this is an artistic conception, but the capture mass, because of angular momentum conservation, forms an accretion disk around the black hole. And then the released gravitational energy is used to heat this gas that is in orbit of the black hole, generates radiation, the disk emits radiation, sometimes winds, and jets. And so all this gravitational energy is transformed into this energy emitted by the accretion disk around the black hole. And the efficiency, when we calculate the efficiency of energy generation from the capture of mass to a black hole, is very high efficiency. So we can show that it's 10% efficiency. Every bit of mass that is captured by a black hole, 10% of the rest mass is transformed into energy, radiative, jets, or winds. And this 10% is a very high efficiency that is much larger than the nuclear energy generation that we know that happen in the center of stars. And we now are trying to control the nuclear reactions to get energy, right? So the efficiency is only 0.7% of energy generation by nuclear reaction. So the accretion of matter to a black hole is much more efficient to generate energy. And then can account for the quasar luminosities, and we can say then that the black hole plus the accretion disk is the most efficient energy generator of the universe.
That is not in gravitational waves, right? Because gravitational waves will go better than that.
Can do better than that? Okay.
Yeah, they can go up to 29%.
Oh, 29. Yeah, okay. Okay.
In light, yeah.
Okay. Okay, so this is new. Okay. So, but the gravitational, okay, generator of, but what kind of energy we can generate with gravitational waves? The amount of energy. Okay, but I mean, if you want if you have a black hole and you send mass, it captures, it will generate energy in the form of radiation and winds, things that we can maybe use to.
Well, the hours we used to move mirrors in an interferometer.
Okay. Okay.
29% is a lot. Which system can emit 29%, can convert 29%?
If you tap on the angular wall, like Planck's knife, it's taking it out of Planck's knife would take it. Well, what if you can do highly spinning black holes merge? Okay, you can go all the way. But so far we've gone up to 5%.
Yeah.
But that's higher than
the vanilla system is even less than 10%. The 29 is really a specific system.
Okay, so good to know. Okay, so my work is with active galactic nuclei, which are similar to quasars. Well, I work also with quasars, but quasars are a part of what we call active galactic nuclei, where you have matter being accreted by a supermassive black hole. In the present-day universe, when you look near the present-day universe, a few million, 100 million light years away, we see that 90% of the galaxies, in 90%, most of galaxies, the black hole is quiet. It's doing nothing. It's just there. But in 10%, the black hole gets activated, and you have an active galactic nucleus. So this means that matter is being captured by the black hole and is producing radiation, producing jets, or winds from the accretion disk. So what I study in this AGN is how the supermassive black hole gets activated, how the mass reaches the black hole, and also the feedback processes of AGN. So which is the effect of the radiation, jets, and winds in the host galaxy. Okay. And nowadays, what we call the supermassive black hole feedback is very important because this radiation and these jets can hit the gas in the nuclear region and even farther out in the galaxy, can push the gas out, and then what happens is that these gas that are in the galaxy would be forming new stars. So if the black hole pushes it out or hits, then you have a delay in the formation of stars or even a halt in the formation of stars. Okay? And now galaxy evolution models need to consider the feedback of the black holes, otherwise they cannot explain the size of the galaxies that we see in the universe. And this is more or less what this cartoon here shows, that the luminosity function of galaxy with the galaxy luminosity. So for the black holes, what matters is this end of the luminosity function. So the observations show this distribution in the luminosity of the galaxies. And the theory without AGN feedback produces more galaxies. The theory of formation and evolution of galaxy predicts much more luminous galaxies than there is in the universe. So the models of galaxy evolution need to consider the feedback of the AGN to lower this number, so the galaxies don't get so many galaxies so luminous as the models predict. Okay? Então, so I would dare to say that if it was not for our supermassive black hole Sagittarius A Estrela, maybe the galaxy would be different. Maybe it would be much larger than it is. And maybe the conditions to form the Earth and life in Earth would not be present. So this would be our connection with the supermassive black hole. So we now see that the supermassive black hole have to be considered when you consider a galaxy evolution. Okay?
There's no feedback from our black hole, right?
No.
It was recently, some feedback, because this new eROSITA image, I don't know if you heard this. eROSITA is this satellite X-ray that made an image, and it shows the Fermi Bubbles. Have you heard about the Fermi Bubbles? So it's a few million years ago. There was some outflow of energetic particles from the center of the galaxy that was seen in the Fermi in gamma rays. Yeah. So now eROSITA, that is in the X-rays, saw also this structure above and below the galactic plane. So it was active a few million years ago.
Was jets from black hole?
Yeah, so two lobes, yeah, energetic lobes from the black hole. So it's something periodic, the nuclear activity. So you have not periodic, but recurrent. So when you have matter falling into the black hole, then you have a cycle of activity.
But there's no accretion disk.
We have a very low accretion rate. So they say that it's a toroidal structure. It's more like a hot ion torus that is surrounding the black hole of the Milky Way, more than a thin accretion disk that you form when you have a very strong or a high mass accretion rate. Depends on the quantity of mass being accreted per time.
So this was seen, this toroidal
No, it was seen just the lobes, you know, the jets, the outflows. Yeah.
So, yeah, all the bubbles exist in the galaxy. I mean, apparently the sun is inside another bubble.
Another bubble, okay.
And that is probably a small black hole, something else.
Okay.
But the question is, how many black holes like that, exist in the galaxy history? Have you an idea?
You mean a black hole like the Milky Way?
Like this one that the sun is inside, because it's probably not too big.
Yeah, I'm not very familiar with it, but for example, I know the statistics of stellar black holes, that is about 100 million for a Milky Way. So, yeah, so we have black holes, stellar black holes in systems or maybe floating around in a large number, 100 million, okay. Okay, so this is one example of an active galaxy, one of the closest, actually is the closest to us, only 12 million light years away, which is Centaurus A. So we can see this is it's an elliptical galaxy that is capturing a spiral galaxy. And this material from the spiral galaxy is feeding the black hole inside Centaurus A that is emitting jets, these jets. So this is a very large region, tens of thousands of light years, even 100. And you have this bubble similar to the Milky Way, this bubble here in X-ray. It's not so different from the one in the Milky Way. And there is these jets in Centaurus A. This is an active galaxy that is producing all this activity. So showing off a bit with the observatories that I used to go. I don't go anymore because you have the space observatories. We do remote observations, but it was a lot of fun to go to the observatories back in the day. So these are the SOAR that is 30% Brazilian. This is Blanco that's not Brazilian, but I think Rogério uses this Blanco telescope for DES, right? And this is the Gemini, and you can see the comparison. It's a 4-meter mirror. He's 8-meter mirror, so I'm here in the bottom. But now we are going to the giant ones. So I have done a lot of work with this technique at Gemini, which is integral field spectroscopy, where you observe a galaxy, both imaging and spectroscopy of each position of the galaxy. So it's a very powerful instrument, and you have also at the James Webb, all major observatories now have these instruments because they are very powerful. You can image a galaxy or whatever nebula in different wavelengths. So, and you can have kinematics. It's a lot of information you get. And also, we can use ALMA. We have a project with a PhD student to observe some quasars with ALMA that got approved. And we got the Hubble. Oh, sorry. And the Hubble and Chandra. All these observatories we use. One example of a study that has some repercussion was this black hole inside one galaxy that MCC 1097 that is 50 million years away. And I was observing the kinematics of the central region of the galaxy, and inside this ring, it's a ring of star formation. This is the ring. And then I was observing with the technique of long slit, several position here. And then in the nucleus, I saw the signature of an unresolved, it was not resolved, it's just a point, disk that is similar to an accretion disk, but it's a little bit larger. And so actually is what we call the broadline region surrounding the accretion disk. So I could see this object from the spectrum of the region. So this is the spectrum. I don't know if you know what is a spectrum. So when you observe and spread the wavelengths of the light, this is a region that we call the H-alpha line, which has rest wavelength 6563. And usually we see these narrow lines, all these things very narrow. This is emission from gas. What I saw in the nucleus of this galaxy was something very strange, which is this double peak structure. It's a very broad line with a double peak structure. And this means you can model this via a ring of clouds surround the black hole with velocities that reach up to 10,000 kilometers per second. Okay? So this is, we have followed this. And so, and we can see the variation of the clouds. So this is a simple model where this disk is actually made of several clouds. And then we could reproduce what we saw in the spectra. So we did this monitoring for many years until almost the disk seems to have disappeared, this disk of clouds. But so this is something that one can do. And I'm following the behavior of these broad lines that you see in AGN, active galactic nuclei. And now I'm participating of a project being done at the Hubble Space Telescope, just finished to observe all this structure. This is a summary of the nuclear structure, but it's very similar to what I showed. We are looking for these clouds. So this is the black hole, and this is the disk, and these are the clouds that answer to variations here in the inner part of the disk. So we study the variation of the nucleus, and we study the variation of the clouds. We do reverberation mapping to understand the structure of the disk and even calculate the mass of the black hole. So this is a very powerful technique, but it's very time-consuming. It's 1 year of observations with the Hubble Space Telescope, obtaining spectra every week or sometimes twice a week. So this project finished the last year, and the papers are coming out. Regarding the feeding of black holes, in 2009, I wrote, together with a former student, this review where I put together all our observations, also observation of others, of how you can feed that supermassive black hole, how you can make the supermassive black hole alive. So what we concluded is that at large sizes, 10 kiloparsecs, if you want in light years, you have to multiply by 3.26. 10 kiloparsec scales, more than 10 kiloparsec scales, which is extragalactic scales. We have galaxy interactions. We see a relation between galaxy interactions and the presence of an AGN. So galaxy interaction seems to be a means to send gas inwards to activate the black hole and make an AGN. And then you have intermediate scale, galaxy scale structures, bars and spiral arms. We did a lot of work also in 100 parsec scales, where we found these structures are in the nucleus. We call nuclear spirals, nuclear disks. And we could do kinematics of this and see that there is some inflow happening associated with these spirals. Okay? So this was most of the work we have done. And here is the structure of the AGN. And this work that I just mentioned is to study the broadline region, which is just outside the accretion disk. This is an example of how we work with the integral field spectroscopy. remember that I mentioned that integral field spectroscopy is a technique that we are using to map the feeding and also the feedback of a supermassive black hole. So here is 3 spectra in different locations over the image of the central 100 parsecs. So what we did was use near infrared. So this is a molecular gas line, H2, and these are some absorption from stars, and this is another, the bracket gamma line, calcium line. So we use these lines and get the kinematics. For example, we get the kinematics of the molecular gas from this line, and we get the kinematic of the stars from these CO bands. And then we look for inflows as the residual between gas motions in this line and regular orbital motion in the galaxy potential. So just to illustrate how we look for the feeding, for example. So here, this is a very small region, 450 parsecs, not so small, but 100 parsec scales. And so from the CO bands, we get the velocities of the stars. So this means that the stars in this side of the field are coming towards us. This means the stars are going away from us. So this is velocity in kilometers per second. And then we could fit a model, a rotation model for the star. But when you look at the gas, molecular hydrogen, you see something different. So you see this like a spiral pattern on top of this rotation. So there is some contribution from rotation, but there's something else. When we do this analysis, subtracting the rotation component, we see that in the far side, we can work also which is the far side of the galaxy and the near side of the galaxy. So the far side, we see a lot of blue shifts, means gas coming towards the center. In the near side, gas going away. And then we see some inflows in these scales, but here in the center, we see the opposite, and then we concluded there is an outflow also. So what happens in the HN, you always have some outflow, and to see the inflows is hard. But in the low luminosity HN, you can see the inflows. And this is what an example of what we have done. Okay. The center, very center, I have to tell about, the first images of the event horizon of a black hole, right? So this is the event horizon telescope, a bunch of observatories observing together in the same source. They observed M87 and also Sagittarius I star. And to observe this event horizon of these black holes, it's equivalent to observe an orange in the surface of the moon. So it's a very challenging observation, okay? So they needed all this. And so when you have this resolution, they could, from the light coming from the vicinity of the passing through the vicinity of the black hole, you form this halo of light deflected by the black hole. So you could build these 2 images, right? So this is the Milky Way one, and this is the M87 one. They look similar, but M87 is 1,800 more distant, but it's 1,500 times more massive. So in the end, you have a similar size image. But M87, for example, the size of this event horizon, the event horizon is actually inside. It's larger than Pluto's orbit, while Sagittarius I Estrela, which is the black hole in the Milky Way, is smaller than Mercury's orbit. So it's very different 2 black holes. So I'll pass quickly. This is just to mention that the Nobel Prize on black holes. To talk, the final thing I want to talk is our work on feedback. So I mentioned to you that feedback is considered now in the models as important for explaining the galaxies, the evolution of galaxies. And so we did some works with also observing with the integral field spectroscopy. This is one radio galaxy. So you have radio jets, you have hot gas, and we have mapped the outflows in the optical in ionized gas. We found an outflow from the vicinity of the black hole of 25 solar masses per year and a power of 6% of the luminosity of the AGN, which is very strong, and this has impact in the galaxy. But on the other hand, we observed a sample of quasars. This is some quasars at 3 to 4 billion light years away. And we have the stars and you have the gas. So the gas is showing the feedback of the black hole, extending to large distances. And so these are some work that we have done, trying to calculate the power of the outflow and comparing it to previous measurements. So this is the mass outflow rate as a function of the AGN luminosity. Power of the outflow is a function of the AGN luminosity. Our samples are these stars. And then what we find is that it's a little bit below the 5% that we found for that radio galaxy that I mentioned. So it's still a little bit lower than we expect to have an impact on the evolution of the galaxy. And we are now looking at higher redshift in the more distant universe, where in the epoch we call cosmic noon, when the universe was more active. So maybe the power of the outflow was stronger then. And also in other gas phases, in molecular and neutral gas, that we are using ALMA for this. And to finalize, just mention some works that we are joining, or, well, the manga, we just finished some work. We are writing a couple of papers still, which is the Sloan Digital Sky Survey, which is a big size IFU in terms of covering the whole galaxy. And also, we are members of LINEA, and we are beginning now to prepare for the first observations with the LSST, the Vera Rubin telescope. And I also have some projects with the PFS, Prime Fox Spectrograph at Subaru. And we have this project that was accepted. The PI was Rogemar Riffel and Marina Bianchim, but I'm a collaborator, to observe the James Webb, which is blowing star formation wave, unraveling molecular winds in AGN. Also is to observe the feedback from winds from AGN in the molecular gas that is observed in the mid-infrared with the James Webb Space Telescope. And this is just one other object. It's not our object. This is Stefan Quintet's, and the top galaxy of the Stefan Quintet is an active galaxy, and we are planning to do something similar. This is the IFU in the mid-infrared, and you see blue shifts and red shifts, and so this is probably an outflow. So we are planning to do something similar, and this first observation showed that this is possible. Finally, the big telescopes that we are hope to use in the future, and thank you. Some water.
Hi, thanks for the talk. I have two questions. One of them is quite naive. If you could go back to that image where you had the elliptical galaxy.
Okay.
I wonder if at that scale, what we are looking at, the other dots in the image that we are looking at, if they are actually either galaxies, stars, or a mix of both.
Which elliptical galaxy?
It's further back. It's a.
Yeah, when I mentioned
that one.
Oh, okay. This.
No, the next one.
The next one. Okay.
No?
No. Okay, I passed. Okay.
That one,
Okay.
yes.
This is Centaurus A. It's an elliptical galaxy that is merging with a spiral one.
All right. So, but the other dots in the image, they are stars in this scale. We are looking at other stars or other galaxies.
No, this is mostly stars from our Milky Way.
Oh,
okay, this is
okay.
it's a bit low latitude, low galactic latitude, so you see a lot of stars in the field.
Okay. And the second question is, you're probably aware of the Penrose process, the Penrose mechanism of energy extraction.
Okay.
And I would like to ask you, as an expert in this field, like, what is the actual relevance of the Penrose mechanism in this astrophysical scenario, right? Is some variant of the Penrose process taking place? Is something similar taking place? Or is it possible that the Penrose mechanism, as it was described originally, is taking place in this case?
Yeah, I'm not familiar with the Penrose mechanism, so if somebody here
maybe I can respond.
Okay.
So prior to the Penrose mechanism you refer to, in the very same paper, there is another Penrose mechanism, which is just the extraction of energy from a rotating black hole.
Yes.
And the models that underpin these jets, actually, well, one of the leading models uses explicitly that method, that Penrose, that process.
Okay.
So it is very much in the foundations of the model.
Oh, okay, yeah.
So this is extraction of energy from a rotating black hole. So yeah, I was familiar with the name, but I know of this process.
The name
so
would be Planck
to
force
produce jets,
Yes.
it's considered to be important. You can extract energy from this mechanism to produce the jet.
Yeah, I think because the Penrose process, I think it's often considered to be something more academic, because you need to have a particle to break up exactly in a very particular way and interact with the black hole in a very particular way to extract energy. And so I was wondering if, like, statistically, you have a bunch of particles, a bunch of gas around the black hole, right? Statistically, one might break up just to the exact way that it needs to break up to produce energy. But okay, thank you. These were the questions.
Okay. So hydrodynamical simulations are very important in order to find out the process of large-scale structure in the universe, as Jessie pointed out in her talk yesterday. And this is one of the main uncertainties in extracting cosmological parameters from observations like the dark energy survey. So the question is, in these hydrodynamical simulations, there are many parameters, and some of them are related to feedback processes. And the question is whether your observations instruct or help to bracket these parameters for these hydrodynamical simulations.
Yes. Yeah, it's one. Again, it's one of the goals of our project is to look for, how big and how effective is the feedback, right? So when we look in the nearby galaxies, I began working with the nearby galaxies, and I ended up finding a lot of inflows and a little bit of outflows. So you need a lot of activity, so large accretion rate to produce enough feedback. Even so, the first sample of quasars that we have worked with are not that powerful. So we are a factor of 5 down. On the other hand, what happens is that we are doing like kinematic studies of the ionized gas. So you have the molecular gas, you have the neutral gas, and you have also the radiation that produces pressure in the medium. And one interesting result that we got from the Manga observation is that with GMOS, we are looking the inner 1 kiloparsec, 2 kiloparsec, 3 kiloparsecs, okay? In the nearby galaxies with Manga, we covered the whole galaxy. And we could find out that with a sample of AGN and a control sample, that the AGNs always have the lines a little bit more broadened compared to non-AGN out to very large distance from the nucleus. So there is some feedback in the form of radiation and heating of the medium, agitation of the medium that is very subtle. with GMOS, we didn't realize that because we are looking for the big feedback. But with MANGA, you could see that the effect is spread all over the galaxy. So it is present. And so, but you know, the quantity is still, it's a bit uncertain. And the models always push to higher numbers. When you see the simulations, they plot these explosions from the black holes and, you know, hitting large. Yeah, it's more than supernova has to be, yeah. And so in the simulation, you see all this, and I'm trying to see in the data, and I don't see those spectacular things. But when I talk with people from theory, they said, no, but this is it's energy. So it's not only ionized gas, it can include neutral gas, it can include molecular gas, and there is the radiation that induces some pressure, and sometimes it's not so easy to measure.
Can I ask a follow-up question? These simulations, how do they account for the presence of the black hole? This is just a Paczynski Vita or something that is approximate that might miss a very important component contribution from the physics itself?
I'm sorry, when you have these expressions.
Yeah, so are the simulations using general relativity?
Oh,
or
yeah.
are they just representing it with a point Newtonian potential that has been slightly modified to capture in very hand-wave ways the role of a black hole?
Yeah, I think it depends on the simulation, but you know, when you do a large-scale one, maybe the relativity is not so well sampled, you know, to the detail of the masses. Mm-hmm.
I have a question. I will. So I'm intrigued by this correlation that you mentioned between AGN activity and star formation.
Oh, okay.
So, but I don't understand which way it goes. I mean, then the AGN activity basically blows away gas from and grip off the gas from the stars?
So, this correlation is just an observation. So, when you count the nuclear activity and you calculate the mass accretion rate, and then you plot as a function of redshift, you know, to see the evolution, it's goes parallel with the star formation rate. And so they evolve together. So one thing, but one is off by 3,300, or so, 3,300 times. The accretion rate is lower than the star formation rate. Okay, so one can understand this via two mechanisms. One is that the same gas that is forming stars, the residual or something, is going to feed the black hole. So they grow together when the galaxy formed and the galaxy evolved. The stars are forming and the black hole is being fed. Okay, so the black hole is growing in consonance with the galaxy. But there is also this feedback. You feedback, and the feedback is you have a cloud of gas, and it needs to cool to form stars. If you have some feedback, radiation outflow, it will disrupt the cloud and won't allow the formation of stars, or at least will delay the formation. And what happens is that it looks like you have a delay between the formation of the stars, because we see some correlation also between the formation of stars and the black hole. But it seems to be a delay because the stars form and then they evolve, they lose mass, and then the black hole seems to be more active. So we do these studies of the stellar population ages together in AGN, and we are concluding that the stars are not really young, they are a little bit older. So it looks like there is a delay between the star formation and the feeding of the black hole.
Now, I was thinking, because there is a curious feature that the black holes that LIGO Virgo has seen, they are in the region of 40-50 solar masses. And the black holes that we see in our galaxy through electromagnetic observation, they are lighter, up to 20.
Yeah.
So that might be related to the fact that our supermassive black hole is not active, so stars are not being accreting so much, so basically our galaxy is going to...
You mean from the gravitational wave from the gravitational waves.
Yeah, we see all the gravitational waves we see, they point to more massive black holes than the one we see in our
Yeah,
galaxy.
I would think that maybe this is a bias of, you know, what the instrument is tuned to observe.
We could see 20 solar mass. I mean,
really?
there's not much bias for a lower mass black hole. I mean, you lose a little bit of reach, but not that much. So it's really pointing to the fact, I mean, it's preliminary. But it seems that our galaxy are kind of lighter black holes. Unless you tell me that the black holes we see electromagnetically are more likely to be lighter than more massive, but that's not true, right? I mean, electromagnetically, we could see 50 solar mass black holes, right? Could we?
50
solar mass black holes, there's no point. There's no
the
problem.
point is that to build a black hole that is, you know, 50 or something, you have to have very, very massive stars, because the black hole is the remain of a star that exploded. So, and you know, most of the mass of the star goes away, and you have, so I wonder, we don't see so massive stars in the Milky Way, and even, you know, Magellanic Cloud, well, where we can resolve stars, M31, Andromeda. So it's an interesting question, because usually these events detected by LIGO, they are very massive and kind of far away, right?
Sure,
it's like a few billion light years.
Yeah, or 100 of megaparsecs. 100 of megaparsecs, so at least hundreds of thousand light years.
Yeah.
Billion light years.
But no, it has to be a few billion to have some evolution. I don't know. But yeah, it's a puzzle. Yeah, I didn't read too much about to see how people explain. But I agree that in our galaxy we see, you know, the stellar mass black holes are not that big. Yeah.
Maybe it's in a handle to relate binary black holes, massive solar mass binary black hole to AGN. Maybe.
You think? Yeah.
Okay. I'm pushing it too far.
Okay, yeah.
Going once, going twice. So if there are no further questions, before we thank Thaisa, I remind you, come down to sign the dinner paper and then stay here outside for the group picture, and now we can thank Thaisa, please.
Thank you.
Sign the dinner paper, please.
No, I don't think so. There was activity in the past. So I think what you're saying, I don't know. But imagine that maybe in order for us to go matter there is a companion that is sufficiently fast. And so maybe when we actually create the that would be like considered. And then the other is if you have two black holes equal mass near the maximum speed, will be like 4% of total mass. The claim was...
Yeah, it's the most energetic converter.
We're not there. And then you could of course, very rare, but if you have harmonic encounters, you could also get, and then the 29% is just, these are artificial, there is a bound, a big bound.
Oh, you're alive.
And it increases
Almost.
Theoretically, awesome.
Sorry? Awesome. Awesome, good. But you go to other places.
about statistical description of the sky at cosmological scale. Please.
And some machine learning stuff. So first, I'll have to say that this is a very technical talk, but I'll try to give a taste for people who are in this audience, for especially people who are interested in observations and phenomenology, for the relevance of carrying out calculations, because this is something that more and more we are avoiding for a number of reasons. And so this is the first part of my talk, some actually rather trivial formulas, but that as far as we know were not known on the literature, that help us understand and describe large-scale structure as we observe it, which is in the past light cone, and not just in some ideal time equals to constant hypersurface, which is some construction we impose on the data. Also, I'll talk about some applications of machine learning just for fun, because it's something we do for fun. Everybody is looking at how machine learning can solve all their problems in life, and sometimes they do solve some things at some cost. So first of all, what we care about when we try to describe the large-scale structure of the universe. Of course, we don't care about the position of any particular galaxy. All we care about is the relative positions of objects in the universe, because that tells us something about how they initially formed, the initial perturbations, but also how gravity and other forces work to bring these objects together in these so-called structure formation, growth of structure. So we care about observing galaxies and their relations with respect in their positions with respect to each other. That is what's going to tell us about the dark energy, nature of gravity, etc. So we map out the galaxies, and they have distances both along the line of sight and across the line of sight, and these are intrinsically different. The universe, of course, is homogeneous and isotropic, but as we observe it, which is in the past light cone, they are not isotropic because along the line of sight and across the line of sight is different for a number of reasons which I'll expose here. So we need to we need to describe something intrinsically in the past light cone, which is something that people knew since forever, of course, since even from Peebles' paper, it's already in there. Many of the ideas that I'll be talking about, I'll just bring some formulas which give us an analytical description of what's going on, which is important. So I'll also talk about the statistical description here, which depends on not only on the covariance of these observables, which are these two-point functions, correlation functions and power spectra, but also about this Fisher description. And why do we care about this? Because, first of all, you need to understand things in some analytical sense, not just to simulate things to death. And which is sometimes our, we have this instinct. We have near infinite computing power, and we want to simulate everything, but we need to actually understand what kinds of informations are being propagated into our physical problem, and we need to forecast the power of our experiments, and it's something that it's sometimes hard to do if you're just simulating things, if you make just a forward modeling of everything. If this is a kind of very costly approach. So what we want is to describe statistically this without trying to impose some sort of artificial volume into our observations, which assumes that there is no evolution in here. So we observe things on the past light cone here, and if we just draw a box and we try to do some Fourier transform of our field in here, we end up having to basically smear out things in some ways, which may not be desirable. So we don't want to assume that the sky is flat, so that we just basically assume that modes along the across the line of sight are just basically just like Fourier modes, which they are not. So this is the flat sky approximation. We need to observe both the large and small scales, and we need to do things on the past light cone. So for instance, just to give an example, so these, we think that the initial conditions of the universe are very much described by a Gaussian field, but we also know that the best models for the universe are not just exactly Gaussian. They must have these interactions, even if it's just from gravity. So we know that the initial conditions are exactly Gaussian. They're almost Gaussian. So there are non-Gaussianities in the initial conditions. To observe these non-Gaussianities, we need not only large scales, but we need sort of to map out the large to small scales. We need the lever arm. So connecting large scales to small scales is important. Large scales, if you do the flat sky approximation, you may lose across the line of sight scales. or you may to correct in some way the systematics that are generated because of that. So GR effects also, so general relativistic effects on large-scale structures also in this category here. So what we are doing here is working towards description in very thin redshift cells. So you don't average out everything inside a redshift shell, otherwise you lose the information along the line of sight and between the slices. But the cost there is that you end up with having many, many slices. The statistics gets complicated, and you may, and then the analytical calculations here are important. So just to set up the problem, again, what we need are these two-point functions, which are either the correlation function in configuration space or the power spectrum in Fourier space. Of course, we can have all kinds of different traces of large-scale structure, and more people are looking at mapping all kinds of different galaxies, halos, AGNs, groups, clusters, whatever you can find out there. So these two-point functions are symmetric in this sense that I'm writing here. So we have tracer I in a radius r, tracer j in a radius r prime. Of course, this is then symmetric under that transformation where you exchange IR by JR prime. So this is a symmetric object. We need to, our observable, therefore, is a symmetric object, and it's something that we have to keep in mind. When you have many distinct tracers, it turns out that you can describe the inverse covariance of those power spectra in a very simple form. There's an analytical form for that. And the only reason I write you this formula that I don't expect you, for most people here to read into this anything, is that we can figure out actually from this formula here that there is a combination of these observables that you can construct that are completely independent of cosmic variance. What is cosmic variance? Is the fact that when you realize a random field in a finite volume, you have a randomness associated with that. That's cosmic variance, a sample variance in a cosmic arena, basically, right? There are some observables, however, which are independent of this, and this is an idea that goes back to Udo Seljak in 2009, and it turns out that this combination is basically the ratios of these power spectra here that can be measured in principle to arbitrary accuracy. So this is the usefulness of these analytical formulas. They give you an insight about what kinds of degrees of freedom you can construct, how you can get your data combined in such a way that you find something, or to understand how something that you thought would not be observable can be observable. Okay, the only problem with the previous formula that I showed you is that usually when we think about two-point functions, we just say, at least in cosmology, we think that when you cross-correlate two different tracers, you think that you just try to use some formula which is basically like this. At least the linear regime, you say that bias is what's driving the difference between your power spectrum and your matter power spectrum. And this means that actually, if you think about it, there are no independent degrees of freedom in the cross-correlations, which is something that people usually assume in one sense or another, but this is sometimes not true, actually, often it's not true. These degrees of freedom can appear, for instance, when you try to describe the structure formation with effective field theories, which is basically the only analytical tool that we have to go beyond the linear regime. But they also can appear physically in terms of environmental effects, things that appear in these cross-correlations, exclusion effects that depend on the type of tracer, and in other baryonic physics. So actually, the most general case, and this is what I'm going to consider here, it's not crucial for my argument here, but I'll assume that in the general case, we just say that it's a nearly Gaussian two-point function, it's symmetric and it has some noise. This is basically the situation we have in cosmology. I'll not assume that the autocorrelations contain all the physical information. I'll assume that the cross-correlations also contain some physical information here. Okay, so this is the problem here. We have some data covariance. So our data points are these xi. You can think of these as all the positions of galaxies in some redshift slice. And the covariance of that has your signal. So this is the correlation function here. This is your noise. And this is your, what we call data covariance, which is also symmetric here, right? So, well, turns out that you have to eliminate the symmetric degrees of freedom so that you don't overcount, double count these, but this is a trivial issue. And you can actually compute the covariance of that correlation function, which is a trivial formula that most people have seen here. So this is basically a 4-point function, which is given by the Wick theorem by this combination here in the Gaussian approximation. So this is basically data covariance squared, basically. So the covariance of the correlation function is the data covariance squared. It turns out that the exact inverse of this object here is also given by the inverse of the data covariance squared, apart from a first term here, which is a completely trivial formula, which is kind of a, it's underlying many of the formulas that we see out in the textbooks, but you know, this is not very often that you find this in such a simple term, but this is what it is. Okay, so this gives us this object here, the Fisher matrix. For those who don't know this, give you the curvature of your likelihood around the maximum. That's what it gives you. So it gives you an idea about how spread out your likelihoods are. So that's a really important formula that you can have here. And it turns out that it's exactly this. So all that you need is to compute, therefore, these inverse data covariance. So again, data covariance is your data points, the covariance of data points, so positions of galaxies. Okay, so all that you need is to invert that. Once you have that, you can substitute back in the formula here, and you have the Fisher matrix, which is something which is really valuable. Okay, all right. So now, what does it mean? So this is basically up to now. I'm not saying anything new. I'm just writing some formulas here. But what I'm going to tell you about here is how to do that for spherical shells along the past light cone. So basically, we are here, and we are the observer here, and we are looking back, and we see galaxies at different redshifts, at different radii from us, and each one of them, you can think that they are sampling a certain time equals to constant hypersurface here. Okay, so this is let's say Ti, and this is Tj, and all that we can see is some slice of that time equals to constant hypersurface. So I'm going to be assuming here that these are thin slices for reasons which will become clear later. So you can think that each bin here basically has some width here. So you see some redshift between some value and another value, which is not too distant, okay? And then you're trying to build a statistics that allows you to get the 2-point correlation functions between objects in this slice and objects in that slice, and I want to call the covariance of that. So this has also a long history. Okay, many of the things I'll say here are related to that history, but I'll show you also some new formulas which shed some light into this description here, which is, again, the only way to go. There's no other, that's basically it. There's no other way to describe if it's not on the past light cone, because this is what we actually observe. Okay, all right, so again, so you can think that these are galaxies in a given shell here, galaxies in another shell there, and you're correlating them. Of course, once you do that, what you are naturally drawn to is that when you have things on a spherical shell, you want to describe them in terms of a spherical harmonic decomposition, and this is how you decompose that. So this is basically the number counts of galaxies in a given shell. So this is shell counts in shells, if you want. So it turns out that there's a very easy way to compute that if you have a finite number of galaxies in a given shell, for instance. Okay, right. So you can then compute the data covariance of that number counts. So this is the fluctuation in number counts, and you can compute this, and you can actually relate it back to both the power spectrum and the 2-point correlation function, which are in here. Okay, so the signal that we want, so basically the angular power spectrum for 2 redshift slices I and j is related to the 2-point function through this formula here. So what we want to find here is an expression for the Fisher matrix of these guys here for arbitrarily small redshift slices. Okay? Like I told you before, that Fisher, which is the inverse covariance of that object here, is given by basically 2 times inverse data covariance squared. So all that we need is to find a way to express this back into that and then to invert that. So you can imagine that analytically this could be a bit challenging. So first I'll do the calculation in real space to show you that it's actually a very trivial thing to do. You can express the correlation function in this way when you do transform into spherical harmonics. The radial part becomes the spherical Bessel functions. So basically, the data covariance here is given in terms of this simple Fourier integral here. And actually, it's a Fourier-Bessel integral here, okay, of this matrix here, Mij, which is basically the power spectrum here, Pij of k, with the shock noise term, which is this term here. Now, it turns out that it's trivial to invert that expression in a true analytical sense. If you remember that these functions here form an orthogonal basis, orthogonal radial basis here, and they have this so-called completeness relation, if you want. It's kind of an orthogonality. So it turns out that the exact integral of, the exact inverse of this expression here is this expression there, where this is just the matrix inverse of that object M, which is this guy here. So trivial to do, very simple. You can show that this is exactly what gives you the inverse of that. So if you multiply that by that, you end up with basically something which is a Kronecker delta for the slices, which is exactly what you need. Okay, so now it's not as simple as that, and up to here, basically, this is not interesting so far. This is something anybody could do, any last year undergraduate or graduate student and first year graduate student in physics working in cosmology could do this calculation here. This is not interesting because there are effects along the line of sight which break isotropy, which are hard to describe. And these are exactly the redshift space distortions.
Oh, you put the harmonic space data. This is connected to the degenerate sense. I mean, harmonic space data means something special because the last slide is talking one slide before, just assuming one more.
Here?
The harmonic space data. So the harmonic space, what do you mean by harmonic space?
Harmonic here is spherical harmonics, is LM standing for the angles, basically. So the harmonic basis is both the spherical harmonics in angle, okay, and the radial modes are the spherical Bessel function. So that's the harmonic decomposition.
Nothing connected with the degenerate sense of solution, right? So the solution are exactly.
Yeah, so this is a complete basis for expanding some scalar along your let's say your shells. So that's a complete, that gives you a complete description which is non-singular at the origin.
Yeah, exactly.
Of course, otherwise you would need the other functions also. But no, this is a complete function for complete series for this field. So, radial information is critical here, and the main reason is because we have something called redshift space distortions, which is something which is very easy to see, and if you haven't seen that, if you're not a cosmologist, you can imagine that you have a certain system here which is going away from you. That's the expansion of the universe. That's what we call the Hubble flow. But inside that structure here, you have gravity acting, and you have some sort of a center of mass here, and things are being pulled towards the center of mass through their own gravity. So this guy is falling a little bit that way, this guy is falling that way, this guy is falling that way. So on top of the redshift from the expansion of the universe, you also have a bit of redshift from the what so-called peculiar motions of these galaxies here. And we, of course, don't see the effect across the line of sight, which is order v square over c square effect. We don't see that. But we see the line of sight effect of that in redshift. So v over c gives you an extra delta z on your redshift, and that gets imprinted on all your structures. So whenever you have some structure here in the middle somewhere, you'll see some velocities flowing either towards or away from that mass. Okay? And what that does to you is that it breaks the degeneracy now. It breaks the isotropy, because now what you see in redshift, which is the only way that you measure distance, is intrinsically, let's say, polluted, or it carries the imprint of those peculiar velocities here. So this figure here shows you what happens when you are in this so-called linear regime, where these velocities are small. They're just starting to move towards the center. Then when they start to get large, they detach from the Hubble flow. That's what we call the turnaround. And then when they move inside and they collapse, then they create these funny figures here that you're seeing. And this is imprinted. So they break isotropy. We don't see the way that we see things along the line of sight is different than the way that we see things across the line of sight, and it has a bunch of different manifestations here in the data. Okay, so I'll jump straight to the way that mathematically this is manifested in the data. If you fold in this redshift space distortions into our two-point correlation function here, what you have is that you go from the real space description to the redshift space, and that is still in the linear regime, okay? You get these extra terms here, so instead of having just those Bessel functions there in that double Hankel transform that I have there, you get these extra terms, which, by the way, this F here, for those who don't do cosmology, this is basically the rate of growth of structure. That's how fast you are forming structure in the universe, and B is the bias of that tracer. So you get these extra terms here, and then the question is, okay, if you want to do a statistical description of large-scale structure, can you now invert this covariance that comes from that two-point correlation function? And it turns out that you can, and the key for resolving that is actually, because we already have a relation, these two functions here, we already know that they are orthogonal. These other guys here, they are not exactly orthogonal. These are second derivatives, so this is not orthogonal to that, so you have to take each piece at a time. So it turns out that you need to solve some integrals. And as it turns out, some of these integrals, they have exact solutions which are trivial. Of course, all of these integrals here, all of these types of integrals here, just in Fourier space, they can be expressed in terms of hypergeometric functions. But it's completely useless to have a hypergeometric function, because if you put it in a computer, what it will do is that it will try to work out some infinite series that takes forever to work out. There's no way that you can use that, okay? So hypergeometric functions are just a way to throw your hands into the air, say, I give up, and there you go, just take that. Turns out that these integrals here, as we have worked out, by the way, two of the people who worked on this project are here, Ian and João. They helped us to calculate, so you can open these integrals up into a series of terms. It turns out these guys have exact expressions in terms of polynomials. Okay, so we looked everywhere in the literature to find if anybody had written this out. I didn't find anything, at least in the cosmological literature. I also looked in some of the other literature out there. Didn't find anything. I'm sure, however, that some Russian physicists in the 1930s or 40s, they knew about this, because this is all nuclear physics. People in the 30s and 40s, they worked all these things out, but I have no idea what they are. I didn't claim that we have written these for the first time, but in cosmology at least, I think it's the first time that it's written, and it's very useful for reasons that I'll tell you. Okay, so I'm sure that people have worked these out. It's not in Watson's book, it's not in any Bessel function compendium, it's not anywhere, but I'm sure people have worked these out before, because these are trivial. Okay, I mean, not really trivial, but you have to work. I mean, it took us a few weeks, months, something like this, but it's there. Anyway, and why are these useful? Because they give us now a very simple description of the data covariance and basically the correlation function in harmonic space with any kind of radial binning that you want to do. It turns out that you can express exactly the two-point function in configuration space in terms of a kind of a double Fourier transform here, this object here, which is exactly given by the same term that we had before in real space, okay? So this is exactly the same term that we had in real space before. So this is, basically if you put F to 0, you get exactly the configuration space result, but you get an extra term here. So you get a boost here from the growth rate here, the F, but you also get a mixing matrix, which is very interesting. And again, I don't think people have noticed this before, that this is a very simple object, and here it is. It's actually, this mixing matrix is given in terms of those functions that we find as a result of doing those analytical integrals, and they are very much diagonal. They're not exactly diagonal, but they are very much diagonal, and they have these expressions. So for L is equal to 10, and L is equal to 80, this is what they look like. So this is Ki, Kj. These are, let's say, the Hankel transforms of xi and xj, the redshift bins. And if you make cuts here along, say, Ki, what you get is a dependence that falls off very fast from diagonal, actually falls off almost exactly like a straight line here, which is really interesting. So you know exactly how they fall off. So this is basically to tell you that in real space, the mixing of the radii, even with small redshift bins, is some very complicated function, which I'll, by the way, show you later, just so that you can visualize. But in K-space, this is very simple. And it turns out that this is the key here. This guy is almost diagonal. When you get higher L's, this is even more diagonal. So basically, if you look at these cuts here, so as you work your way inside here, so these outer lines here are for L is equal to 10. Then the second line inside here is L is equal to 20, then 40, then 80. So they fall even faster. So in Fourier space, these guys are basically, so again, this is just the purely radial contribution from redshift space distortions to the angular power spectrum. So it's these functions here. So they are almost exactly diagonal. And this is what enables us to go back and describe things in an approximate way, because now, you know, the off-diagonal terms are just a correction. Now you can make basically a perturbative expansion, take the off-diagonal terms, and then you can basically make an analytical calculation from then on. This is, by the way, what you get for the same thing in configuration space. This is a mess, okay? You don't have an analytical formula for this, but this is basically what transforming back from Fourier space to real space gives you. It's a mess. And as you have smaller and smaller redshift slides, it becomes more and more of a mess. And this is just for a single mode, by the way. If you have more modes, it becomes even more of a mess, okay? Of course, you cannot invert this kind of a thing if you have, you know, say if you have 100 by 100 here. Okay, there's no way you will invert something like this. I mean, you would need a huge amount of, that's just for 1L, by the way. So with thin slices, there are many, many more values here. Remember that the correlation function gives you, so you can think of this. Imagine that what you want to do as somebody who is trying to connect theory with observations is that you want to map out each point of this matrix here. So if you have 100 redshift slices, this is 10 to the 4 divided by 2 points that you need to map out. So this is your observable, these 10 to the 4 points, basically. And you need to know the covariance of those 10 to the 4 points with all the other 10 to the 4 points. Think about this as a numerical problem, and you immediately realize that it's hopeless, right? You would need millions and millions of simulations, which of course you don't necessarily want to do. So, so the problem is that we want to have the thin redshift slices because we want to keep the information along the line of sight. Otherwise, you smear out the redshift space distortions. You lose information. You don't want to do that. But the cost for that is that your problem becomes of a huge, huge order. Of course, you cannot deal with such a huge dimensional problem with numerical stuff, but you can with analytical approximations. That's exactly what they are there for. So what I want to do here is that I want to consider the case where you have many, many redshift slices, and you have the the angular power spectrum for very, very thin redshift slices, and I'll show you the formula for the covariance of those guys, okay? By the way, these kinds of objects will not be diagonal at all, but they'll have a structure that we can resolve analytically. This is, by the way, here, what you get for the covariance of the angular correlation function in thin redshift slices. How many redshift slices did we use in this exercise again? Do you remember? 40, 25, 25. This is just with 25 redshift slices. This is the kind of covariance that you have. And if you want a Fisher, you would have to invert that. Good luck with that. That's just 25 redshift slices. Of course, you want more than that, because you can imagine that if you have a spectroscopic survey, you can have hundreds, maybe even thousands of redshift slices. So this is the covariance just for L is equal to 10. So this is what we have computed in a sort of simplified model in theory. This is also what we simulated here with, I don't know, João, how many simulations did you have to use? Thousands and thousands and thousands of simulations, right, just to have this. And this is a very simple model that, by the way, has a nearly analytical expression here. So I just submit to anybody that has ever work with data that if you want to use some covariance matrix like this, it might present a challenge, right? So how do you solve for this? Well, you go back to the expressions that we had before. So basically, this is the data covariance that has your, take the hand out of here, has the off-diagonal terms in here. So you can rewrite this as a purely diagonal object plus some off-diagonal terms. Then you can plug it back in, and you can write the expression for the inverse as a perturbation series like this. So it has shot noise. It has diagonal term in Fourier space, and then it has the first corrections from the off-diagonal terms, which are in here. They depend on this guy here. But these are all simple expressions. They are, the only trouble here are these Fourier integrals here, which we have calculated using codes called FFT log, which compute very fast integrals involving these Bessel functions. It turns out that even these integrals here you can solve within a matter of seconds, even these Fourier integrals here, the double Fourier integrals here. Okay, so just to give you some background, if you wanted to compute this here on the basis of simulations, you would need an absolutely humongous amount of computing power, not only to compute to make all these realizations of your maps, but also to compute the covariance. You need to keep up a huge amount of data in your computer. So this is basically doing this even with flask or glass, impossible. There's no way that you can do this with more than, I don't know, I don't remember. Artur is the guy, Artur Loureiro, our other collaborator, is the guy who gave us the number, but I think it's with more than 15 or 12 slices or something like this. It's just impossible to do with Flask or even the new version, which is called Glass, which I think they are about to release. But you can do this analytically in the linear approximation. So basically, once you compute that with that formula that I just gave you, which is, again, a matter of seconds or minutes, if you want to have L from, say, 4 until 100, okay? So this is what you compute here. You plug that back in, and you have a Fisher matrix. And then you can do everything that you do with Fisher matrix. For instance, in power spectrum, you can plug it back in a Fisher code, or you can plug it back in a Monte Carlo, whatever you want to do. So what we assume here is Gaussianity, linear regime, and full sky. Full sky is not so important because you can actually have partial sky, use pseudo-CLs, and then there's a mixing. You can make bins and Ls, and that's pretty much the same thing. You treat a bin and L just like an L. It doesn't matter too much. But these two are key assumptions. However, if you think about any Fisher calculation that have you ever done in your life, you assume that anyway, so that's not a really critical assumption here. I mean, at least not different from what we usually do. And also already gives you a first step if you want to correct for some nonlinear stuff with starting with an analytical formula.
So linear is because you use the linear power spectrum, that's all?
Yeah, I'm using redshift space distortions in the linear regime. Okay? It's an interesting question about what if you can fold into your model some nonlinear redshift space distortion model. Beyond Kaiser, I don't know, I haven't done the calculation, but it might be possible. I don't know, but I don't know about that. Okay, so basically, this is a simple and straightforward. It doesn't look that simple, but given a certain model, which you always have to provide a fiducial model there, the integrals are actually straightforward with the present tools that we have. So the question is, to what accuracy do we need these? Can we somehow use the Lieber approximation to simplify those integrals?
Like Lieber. If you look at the approximations there, the first term with the delta function looks like Lieber.
Yeah, so the second term would be beyond Lieber in some sense, but it's beyond Lieber. Yeah, it's something like this, but it's, yeah. So maybe the second one you can approximate with Lieber because they also have these integrals in there. Yeah, that's basically the idea. That would be to make it even faster. Anyway, so so the question is then how we now go to some nonlinear scales, how we incorporate other effects like lensing and other things, which I'm not very optimistic about how we can incorporate effects which are integrated along the line of sight, because then these lead to complicated radial integrals that kind of not sure. I'm not sure about this. We are looking into this, but I'm not very sure if we can do this effectively. Okay, so what is next here? Question is, why would somebody use something like this? I mean, why do you care? Why have you made this calculation? First of all, I've made this calculation because it's possible. and eventually, if you have an analytical description, somebody will use it eventually, because it has to be there, and it's the basis for anything else. So anyway, so there it is. Now, it may be useful in the following sense. When we are now more and more trying to observe large-scale effects like non-Gaussianities, like GR effects, testing gravity on larger scales, etc., we need to go to connect both the large scales and small scales. If you just smear things out along the line of sight, you are losing information, you're losing small-scale information. It's not clear to me that you're going to get as good constraints that you could have. And it's not clear to me that you would not be biasing your evaluations if you're just assuming that you have if you just put a box in there, you assume that there's no time evolution. It's unclear. So the next step, and this is the project of one of my students here, João, is to calculate, to have a very nice toy model where we can both do the complete parameter estimation both in Fourier space and in harmonic space to map out the ways in which you delimit the problem. So small scales, everybody knows that the small scales you have to eventually cut off from your problem. You have to put some limits to how much on small scales you can go. When you have Fourier description and harmonic description, small scale means something different, right? But there's a way to map these two problems, and then we can compare, and we can see if our parameters are equally well estimated in both approaches, and if there are no significant biases in them that appear as a result of imposing Fourier or not. Before, this calculation would be impossible. Now that we have an analytical Fisher matrix, it's possible. At least we can figure out if there is relevant information in a harmonic description, which is lost when we go to Fourier space. May very well be that there is none, and we're just making a lot of trouble. But this is the question here. So how does the harmonic description compare to Fourier space? So this is basically the next step here. Okay, now for the second part of my talk, which may be more fun for many people here, which is using machine learning to do a lot of stuff that we like to do and we don't have the patience to do if we don't have infinite time to sit on our problems. So more and more people are using this. Actually, as far as I understand physics and astronomy, there were some early papers in the end of the 90s, I think, beginning of the 90s actually, but it wasn't really adopted a lot, and I think physics and astronomy are a bit of a latecomers for this. Actually, in many other areas, people have used this a lot, but physics and astronomy is only in the past, I don't know, 4 or 5 years that it's exploded, and now everybody's trying to do everything with that. I'll give you some examples of what you can do here. So this is actually connected with the question to Thaisa earlier on. We have these simulations where you have dark matter and baryon physics, and you have galaxies emerging out of those simulations. It turns out that to a very good extent, you can just use the dark matter information to predict the properties of the galaxies that will form in a given dark matter halo. It turns out that using these machine learning methods, which are really good for tackling these very complex problems with hundreds of variables, highly nonlinear relations that you couldn't possibly describe in any analytical sense, you can train certain code to use the information about the dark matter to predict the properties of the galaxies. And to a good extent, this is what people are being able to do. So in some sense, to a number of properties of the galaxies that you have in your volume there, you may not need full hydro simulations if you have large enough sample of simulations that you can train. Then you just give some dark matter simulation, and then you paint on the galaxies. There are many models that people have used since forever for this, like models and so on, but machine learning does this much better than all the codes that have done before. The only problem is, like the question for Thaisa, is that on these models here, the way in which the simulations, the hydro simulations, implement baryon physics is imperfect, and they assume some small-scale effects, which we don't really know, actually. So there are some unknown physics going on. You can train with different kinds of models for the baryon physics, and out come slightly different types of galaxies. You can kind of smooth out these things and introduce some error because of that. So this is a paper with my students Nathalie and Natalia that predict properties of the galaxy. So the true properties are here in the contours, and the predicted properties are here on the color lines here. Another thing that we have played with is this, the notion that machine learning is a black box. So anybody has, by the way, let me make a kind of a poll here. Who here has played with machine learning in any sense? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So this is mostly, I would say, more of a theory-oriented crowd, right? So that's a lot of people, right? Okay, so if you have ever thought about this, looked at how these machine learning codes work, they are a completely black box. Forget about understanding what goes on inside. That's totally beside the point. The output of a machine learning code is, let's say you want to classify objects. You give pictures of cats and dogs. You want to say, is this a cat, is this a dog? It gives you a score. This is a score of 0.8 for being a dog. This is a score of 0.9 for being a cat, or something like this. Now, what is a score? Score is something that's spewed out from the code. It's not a probability. It will never be a probability. It has not the sense of a probability. Now, how do we as physicists work with something which has no sense of being a probability? How do we deal with that? What is the probability of something that I'm observing here in my data, that it's a galaxy, star, that's a quasar? If all that you give me is a score, how can I then fold that into the information that I have? Because it's on the basis there, right? So there is a connection which is very, very far from trivial between machine learning outputs and probabilities. It turns out that for almost all of the machine learning community, errors do not exist. There are no errors. People just give, what is your height? It's 180. 180 exactly, 180,000. They just write that. There's no errors anywhere. Or they assume that the errors are all the same for all the data points that you have. A lot of machine learning, I would say 99.9% of all machine learning literature is based on the assumption that your data is categorical. There's no error. Okay? Now, it turns out that errors, of course, are on the basis of any statement that you do about signal and noise, and therefore of the relevance of the data points. And we've done here a quick study of how including the errors make your whole machine learning code work better. So it turns out that machine learning codes, they can be tuned to return you something which is almost a probability. So you train them to see probability, even if they have no sense of what a probability is. But for that, you need to give data to the machine learning which has errors. Otherwise, how would it learn about the errors? That is a basic point. But it's very much lost in much of the machine learning literature. And we, in this paper here, showed how when you include errors, basically you turn the scores of the machine learning into basically a one-to-one function that's related to probability. So they can be mapped through probability. In the absence of errors, basically, you have zero correlation. And your score is anything. All right? So if you're just doing some task with machine learning and you think your score is a probability and you're assuming that, look at this figure. So this is the true probability, which is calculated with a Monte Carlo. And this is the actual, let's say, score of your machine learning. It has no relation. It's just completely unrelated to that. So if you want to have a sense of probability, the basis of that is in the measurement, is in the input data. If you don't have any errors in the input data, there is no probability anywhere. It's not in the beginning, it's not in the end, it's nowhere. Well, finally, just how many? I have 0 minutes, I guess, right?
No, 4.
Okay, so that's time enough. Another application that we have done here is, again, going back to the covariance matrices. So basically what we have here is that in large-scale structure, true simulations that actually reproduce your structure formation in all scales or even without baryon physics are extremely expensive, okay? If you want to simulate a cosmological volume on scales small enough to resolve even, let's say, a group, individual subhalos in a halo, you need an n-body simulation, which is hugely expensive. So if you want to have your observables and you want to give a sense of the covariance of those observables, so the probability, you need many simulations. Now, typically, we need to compute, if you're just doing the simplest thing you have, which is power spectrum in Fourier space, which has a nearly covariance, nearly diagonal covariance, what you get here with, let's say, 50 cosmological volume simulations is something which is as noisy as what I'm showing here to you. And you need to know that very well, okay? So how do you do that? So we had this idea here with my student Nathalie that we could actually use the generalization power of machine learning to teach a certain code to denoise covariance matrices. So basically what we have done here is that we use cheap simulations, what we call mock generators, to teach the machine learning code how to clean this covariance matrix so that it becomes equivalent to the covariance matrix that's produced with thousands of simulations. And then we apply that same code to a covariance matrix that's produced with very expensive n-body simulations. So basically here, we used Cola type mocks to train the code, and we applied to the Pinocchio simulations, which is basically the only simulation we have out there in the universe that has literally thousands of n-body simulations for the same volumes. So we know what to expect from this when we clean it up. We know what the result here has to be. And it turns out that machine learning is incredibly accurate at doing that. So you start with here. So this is a measure of, n here is your sample size. And here is a measure of your noise. Let's say this is your residue. So it's the level of noise in your covariance matrix. So of course, when you have very small samples here, have very high noise, as your sample increases, your noise level goes down. So when you apply this denoiser, which is basically an encoder, you lower the noise level here, and a sample which has about 50 maps, 50 volumes, becomes as good as a sample that contains about 500 simulations. And when you have more, this becomes 800, 700, 1,000. So you can basically, with very little cost, get something which is, for the price of 50 simulations, you can get something which has basically is like 500. Something else that you can do with machine learning. Of course, these things have to be tested to death, otherwise you might very well be doing some crazy stuff to your covariance matrices. But this is, again, on the basis of pretty much anything that we do in cosmology, because covariance matrix is what you feed to your Monte Carlos, is how you fit parameters in the end. So having a less noisy covariance matrix is critical. And here are some figures that we have done here in this paper that show you how a sample of 100 simulations here gives you some bias in some parameters like omega c, like the bias and other parameters. And when you denoise that, you get basically back the exact parameters that you would have with a much, much larger sample size. So again, that shows you that the machine learning is not biasing is not introducing, it's not skewing your covariance. It's not introducing spurious structures in your covariance. Okay, so I'll stop there because these are conclusions. I'll probably just go for the questions. Thanks.
Hello, thank you for your talk. 2 questions. I don't think they're very hard to answer. The first one is, you mentioned how for low L's, the Fisher matrix stops being nearly diagonal. At least they stop. The approximation is not very good. Does this have anything to do with cosmic variance?
for low L's, not sure. I'm not sure. I haven't thought about this actually. For low L's, you are averaging out an angle over big volume, so it's like you're correlating larger distances. So you expect things to be more correlated inside a given volume because you're averaging out over larger distances anyway. But in the end, it's a bit like this. You're talking. What is the size of your volume? Is the size of your shell, right? So for lower L's, you are averaging out bigger chunks of your 2D sphere. So in some sense, things are more correlated. So that's pretty much the same as cosmic variance in some sense. You have more variance for the long wavelength modes if you want. So yeah, probably it's the same thing. Probably it's the same statement, although I haven't thought about that. Thank you for the, for the thought.
Thank you. And the second one, when you mentioned when you include the first order corrections to the line of sight and the radial functions for the redshift space, where we have the derivative of the spherical Bessel functions. Yeah, exactly, perfectly. Do these HL and GL functions have anything to do with the green functions of these?
The what?
The green functions of these JL and their derivatives? Because
well, in some sense, what you're doing is you are, you can think of each redshift slice as an impulse in that sense, right? So you are, it's, I guess in a very broad sense, you can say that this would be kind of if you integrate over these functions with the redshift cells, what you get is the covariance. So in some sense, maybe, but I wouldn't go as far as that because we don't really have a second order equation, linear equation that we're solving in a usual sense. So it's not, although the interpretation is similar, right? Yes.
Okay, thank you.
Thanks. So all of this, the derivation here is for infinitesimally thin redshift shells, is that right?
It's for very thin shells,
okay.
Yeah.
If one wanted to do this calculation for redshift shells that had some width, does this formalism, like, is there a way to extend this?
Yeah. No, the calculation in the paper is for finite shells. All that you need is that you assume that there is no evolution within each shell. If there is evolution within the shell, then the calculation doesn't work. But all the formulas in the paper, this is simplified for for a presentation. But on the paper, it's all for finite shells of a finite width. So there's a volume, there's a radial bin width. But they only work if you assume that within the shell there's no evolution. So all the quantities within the shell are at a time equals to constant hypersurface effectively. Yeah.
Thanks.
Okay, very interesting talk. I have a question. In your treatment of distortions, have you also considered Alko-Paczynski distortions, or they are not significant?
Well, this is kind of a, this is not a angular distance versus luminosity distance question, really. But they are all in the same category of things that break isotropy in some sense, right? So if you look at this, figure here, you can think about this in the radio and across the line of sight as a kind of an Alko-Paczynski, because the way that you measure these structures here, which are the BAL scales, is that you can think of angular and radial. The way that you measure them is intrinsically different because you're using a sort of a angular distance and radial distance, and this is kind of an Alko-Paczynski. In the sense that I'm telling here, no, this is just the effect of peculiar velocities and the projection of that. No, I would say that it's a simpler case.
Okay, thank you.
I mean, that's my interpretation. I don't know about you guys if you think that there's a. I mean, people call many things Alko-Paczynski. I don't know. Sometimes it gets a bit fuzzy. Yeah.
Yeah. Thanks, Raul. Really nice talk. I I should probably look at the paper, but the last thing that on the second part of your talk, when you showed this figure with the MSA, which is I think the mean squared error of the associated with the covariance matrix, probably. Yeah. Okay, that's one thing. The other thing is you showed the Wishart analytical computation.
Yeah, I didn't say anything about that. That's
no problem.
If you want, I can explain now. Now that you asked, I have to explain.
My curiosity is why the points are always above the Wishart? Yeah. There's a.
So what you're seeing there is the expectation value and the 1 sigma width around Wishart, right? So I think that, we're actually doing a kind of I think 1 gigaparsec volume, computing the power spectrum inside, so there are many other effects in there. I'm not sure that the Wishart is for a certain Wishart formula. So Wishart is a kind of a PDF for a covariance matrix, assuming, making a lot of assumptions. And I'm not entirely sure that all the assumptions are true for the power spectrum that we are computing on the basis of really simulating something, measuring the modes with some band powers and so on. And it's not clear that all the assumptions are true. So maybe the fact that we get a bit higher is reflecting that. But it's like 1/3 of sigma away from that. So I don't know how significant that is. Yeah, so just for you guys to understand, so the gray line is an analytical formula called the Wishart distribution. By the way, Elentine, who would be here, is the specialist in the world about that. And anyway, she corrected some of the stuff in the literature about this. So yeah, so that's just to, that curve there is just to give you an idea of how you would be effectively enlarging the sample by using machine learning to clean out the covariance matrix. That would be effectively augmenting the sample.
It's really nice.
That's basically it. It just serves that purpose. It's not really, it's just to guide your eye in some sense.
Right. It's super nice.
Yeah.
And then I should begin with this question. You are denoising the covariance matrix.
Yes, the covariance directly
on the precision matrix. You are doing that directly on the covariance, not in the inverse of the covariance.
No, I'm doing that in the covariance because that's what you compute to start with before you do anything like precision or anything like that, right? I mean, I would say that cleaning out the covariance is much safer than computing a precision and then cleaning out that, because if you compute the precision from an inaccurate covariance, then you have already introduced some nasty stuff in your problem. I would think that this is, I don't know, that's a good question, but I would say that I would be very surprised if working in the precision matrix would be better than working on the covariance and then working away later to the precision. And by the way, this is basically here, this is a manifestation of the precision matrix, right? Yeah. Right? So this is the precision matrix in practice after you put that in your Monte Carlo. Yeah.
So I have a question dovetailing this last one. So it's a provocative question. It's a bit long, so let me just describe it a little bit.
I'll sit down.
So in numerical simulations, so people, depending on which camp, will present the result as if this is correct because it looks right. Other camps don't have the luxury of dealing with fields that naturally have an interpretation. Well, so it's hard to say it looks right. So you have to go work hard to show the error is this, and this is why we trust the solution. So in the context of machine learning, we're starting to grapple with this. So I always point to, and I think those of us that have worked in one way or another in machine learning have this challenge in front of us. So I typically send students that want to do numerical simulations, say, well, go open the book by J.P. Boyd. It's in Spectrum Methods, and look at definition 16. It's either 16 or 17, depending on which edition. It's a pretty cool book, has lots of interesting snippets here and there, but definition 16 or 17 is the definition of an idiot.
For what?
An idiot. And it goes basically, an idiot is someone that presents a numerical result without having done A, B, and C, right? And that's very good because it tells you at the end of the day, this is the error that this particular simulation would have. So we need a definition of an idiot in machine learning. Do you have one?
Definition of an idiot?
Yes. If you publish a result, so what you typically see is we've trained with this many sample sets. This is the result. Okay, how do we know we should trust it? To what degree? So you're going after it with this.
I have an exact definition of that. If you don't know, if you cannot even tell the difference between a machine learning score and a probability, then you're an idiot. If you don't know how the uncertainties in your data, in your method, or in your model, or in your theory, how that propagates your uncertainties in the end, then you are an idiot. And I would say that this is the beginning only, right? And if you don't test to death the end result with all the ways that you can measure how some black box is skewing or biasing your result, then again, you are an idiot. I would say that there are multifold ways of being an idiot, but it starts with realizing that machine learning is a black box, and that, however, that it will be more of a black box if you hide from it the uncertainties in all your assumptions and your data. So just the fact that more than 99% of the machine learning community doesn't even consider that errors exist means that there's something wrong. Of course, for many things, these are categorical things, right? It's 1 or 0, exist, do not exist. So how much money you have in the bank, it doesn't have an error, right? But, I mean, everything else is uncertain, including the model that you're using, including the many assumptions that you are kind of building into your system. So, I mean, there's no way around it. So if you want to do any kind of a science-like prediction in the end that carries a certain weight of certainty, you wanna make a discovery, it's 5 sigma. Okay, I don't have an idea what a sigma is. Then you don't have a discovery, right?
Thank you.
I hope I'm not an idiot, but I'm not sure.
That was very clear. Okay, one very last question before coffee. So be quick, because you're keeping us from coffee.
No pressure.
So thanks for the talk. In the second part, where you talked about machine learning, at some point you showed the score prediction versus a real simulation. And I did not actually, and you presented, you said the errors, introducing errors actually fixes this problem, but I did not actually understood the moving parts of this experiment. Could you?
Okay, so it's very simple. Okay. We have curves here, which is basically a parabola, and it's either up or down. This is actually called the smiley, frowny model here. And your points here, they are representing measurements. Yeah. Some measurements have small error bars. Some measurements have higher error bars. Okay. There's no way, if you don't tell them, if you just put the points there in the machine, it has no idea which points are relevant, which are not. Okay? There's no way that it can infer from anything. So you're making the black box even more black, even more opaque. Okay. So we have a kind of a Gaussian distribution for pretty much everything in here, both all the parameters. So we know exactly, actually it's an exactly integral model. We can compute analytically the Fisher matrix in this case. That's another good thing here. So we know exactly what these probabilities are, but we can also do a Monte Carlo calculation for the likelihood that an object is a type A or type B, if you want. Okay. So this is the Monte Carlo here, which is an exact posterior in that sense. Okay, we control everything in the system. Okay. And we compute also the machine learning confidence here in a variety of methods when we do not include the error bars and when we include the error bars. It's still a black box, but the black box without the error bars is incapable of inferring what is anything like a probability, whereas when you give the error bars, you get this. You get it's not a line, but it's a one-to-one relation that can be mapped. Here, it's not in any sense a curve. In this case, it is a curve. So it's a sort of a nonlinear transformation that given one, you give the other. In this case, it's impossible without feeding the errors into the system.
So the errors are actually fed into the machine.
Yeah. So here in this case, you just give the points without the error bars, and in these two, in this other case here, you give the errors together with the points. So you feed into the machine learning the points, data points with the errors. Okay. And it's slightly more complicated how to do that, but you can do this. And since it's a very simple system with basically a Gaussian realization, we could do zillions of these things. So we have a very good, we can map these figures to exquisite accuracy, and so we can say, okay, now a relationship emerges that wasn't there before. But it doesn't matter how many simulations you have, it doesn't matter how you augment your data set, it doesn't matter what to do. If you don't tell the system what your errors are, it cannot infer that. It's just as simple, it's obvious. Anybody has, first year student in physics knows this, right? If there's no sense of uncertainty in your measurements, then whatever conclusions you have in the end, they have, I mean, what kind of a meaning do they have? They have zero meaning, right? It's as simple as that. But amazingly, the vast majority of machine learning community doesn't even think about errors. They don't exist. Maybe for good reasons, but often for very bad reasons. They just used to doing things like this.
Thank you.
But yeah, I'm not, by the way, the only person who has done this. Many people have used this, even in astrophysics, but it's very far from the norm.
Okay. I was interested about the architecture of the machine learning. How do you?
I can tell you, yeah.
Okay.
Okay,
So
I've abused your time. Thank you.
So we reconvene at past.
Thanks. Yeah.
I'm your man.
Ricardo Sturani is involved also not just with the organization of the workshop, but helps also with the prize. And there are 3 or 4 international people that, okay, Luis can tell us who.
So the members of the committee were Walter Goldberger from Yale. He's originally from Venezuela. Vitor Cardoso from the Instituto Superior Técnico in Portugal. He's Portuguese. Rodrigo Fernandez from the University of Alberta. He's originally from Chile. Gabriela Gonzalez from Louisiana State University. She's originally from Argentina. And Marcel Soares Santos, who is at the University of Michigan, originally from Brazil, and myself. Of course, maybe I'll say just a couple of words. This is a brainchild, this prize is a brainchild of Ricardo Sturani, who came up with the idea and talked to Nathan, and Nathan thought it was a great idea, and he and the Institute supported, and this has been great. I mean, as a member of the committee, I can only say it has been great reading all the theses, and this has been seconded by every member of the committee, so much so that this year I said, well, at some point we need to start changing the composition, but everyone said we would love to keep doing this because it's a great opportunity to see what's going on, help the institute, help the local scientists, and it's a great initiative. So I wanted to say before we start, a lot of thanks to Nathan and ICTP-SAIFR for the support, for this idea, for helping it. It's great to have examples of special places that pick a good idea and push forward, and ICTP-SAIFR is doing an excellent job, not just for the physics of Brazil, but as you know, for the physics of South America as a whole. So I'm very happy to be involved in any way I can. And okay, so let's get going. Yes, so we're gonna call the people, just maybe, and then we're gonna ask you to sit there, and there will be a picture.
People who aren't here.
So talk with the, well, let's go with the people that are here first. So let's say the winner, so this took place in 2 years, 2020, 2021 and 2022. Because of the pandemic, we couldn't have a workshop last year, so we are joining both this year. So the recipient of the prize on 2021 is Carlos Correa. The recipient of 2022 is Iara Ota. And we also, I mean, the quality was so high that unfortunately we had to pick winners, but we couldn't just say this is where it ends. There are honorable mentions, people that had a very, very strong contribution as well. And so we have 2 of them here today. Marcos Argañaraz from the year 2021. And Caroline Wandalin, this year 2022. And then just for completeness, the other recipients of the honorary mentions are Leonardo Gianni, Jorge Enrique Garcia Farieta, and Eduardo Becerra. So congratulations to them as well. And now we have the pleasure to hearing from them some of the material that was in their thesis. So we're going to start with Carlos. Thanks.
Okay, can you hear me well? It's okay. Okay, well, first of all, I want to thank the organizers for inviting me here. It is an honor for me to receive this award. Today I'm going to present the main results of my PhD research about cosmic voids as cosmological laboratories developed at the Institute for Experimental and Theoretical Astronomy in Cordoba, Argentina. Well, this is my team. This is Dante Paz. He was my PhD supervisor. And the other ones are my collaborators, Ariel Sanchez, Nelson Padilla, Andres Ruiz, and Raul Angulo. Well, let me start with some introduction and the main goals that we pursued in my projects during my PhD. Okay, so in the last decade, we have entered in an era of high precision cosmology. Modern observations show that the universe is not only expanding, it is also accelerating. The standard model of cosmology postulates a flat lambda cold dark matter universe in which this cosmic acceleration can be explained by introducing a new component known as dark energy. From a theoretical point of view, dark energy can be associated with a cosmological constant in Einstein's field equation, which can also be associated with vacuum energy. But alternatively, this could be a hint that we need to review our fundamental laws of gravity, I mean general relativity. Even worse, dark energy is the dominant component of the universe. It contributes to almost 70% to the total energy budget of the universe. So this dark energy problem is one of the major challenges of modern cosmology. Okay. So up to date, the three most important dark energy experiments are the following. The Hubble diagram using distant supernovae 1A as standard candles, the study of CMB and anisotropies, and the Alko-Paczynski tests using the BAO scale as a standard ruler. So here in this plot, you can see the cosmological constraints for over two fundamental cosmological parameters, omega matter and omega dark energy, for the three experiments. Two important conclusions can be made from this plot. First, that the constraints are consistent with each other, even though the experiments are independent with each other in the sense that they contain different physics inside. And the second important conclusion is that the constraints have substantially different orientations. So a joint or combined analysis allows us to put even tighter constraints to the parameters. So what is the goal that we pursue with cosmic voids? Well, it is to incorporate tests based on voids to these cosmological toolkits in order to see if we can put even tighter constraints to the parameters, or even if we can detect any tensions with the model, with the standard model. Voids can be used for cosmology in many ways. But here, for this presentation, I will focus on two statistics, the void size function and the void galaxy cross-correlation function. But before that, a simpler question. What are cosmic voids? Well, we know that galaxies do not distribute randomly in space. Instead, by the action of gravity, they group together, forming different structures, like groups of galaxies, clusters of galaxies, and even larger structures, like filaments and walls. But complementarily, in this process, galaxies live on their way vast underdense regions. These are the so-called cosmic voids. Here in this map of the Sloan, the darkest zones are potential cosmic voids. Okay. The statistical properties of voids depend on two conditioning factors. The first one is the type of tracers that we use to identify voids, namely galaxies from a survey, or dark matter halos, or dark matter particles from a simulation. And the other factor is the method that we use to identify voids from the spatial distribution of these tracers. Although there are many classes of void finders, there is a consensus on the basic properties of voids. Roughly speaking, we can say that voids are underdense regions with a density of 10 to 20% of the mean density of the universe, and with sizes in the order of tens of megaparsecs in diameter. And the last question to finish this introduction, why cosmic voids for cosmology? Well, on the one hand, they are the largest observable structures, so they encode key information about the geometry and expansion history of the universe. Moreover, their dynamics can be treated in the linear regime quite well. Furthermore, they are ideal for testing modified gravity theories, mainly because of the unscreening mechanism in underdense environments. And finally, modern spectroscopic surveys are mapping the universe, covering a volume and a redshift range without precedence, which allows us to obtain rich samples of voids. Now, for the second part of my talk, I will go deeper into the phenomenology of voids. Okay, so as I mentioned in the introduction, a key aspect, a central aspect in all void studies is the method that we use to identify them. For all my work, I used the so-called spherical void finder. It is based on the integrated density contrast of underdense regions, assuming spherical symmetry, and with respect to underdense locations of space. Here you can see the main steps of the algorithm. I don't have time here to explain them in detail, but what is important here is the final output here. The method returns a catalog of voids with the following characteristics. They are underdense spheres that do not overlap, with a well-defined radius and center, motivated by physical considerations, from which an isotropic outflow of galaxies is observed. Okay, so now I am in conditions to introduce the first void statistic, the void size function. Mathematically, the void size function quantifies the comoving number density of voids as a function of their size. This is a fancy way of saying a histogram of void radii. So physically, the void size function describes the abundance of voids in the universe. It is analogous to the dark matter halo mass function, so it can be modeled in a similar way using the excursion set theory combined with the spherical evolution of density perturbations. So there are three main approaches for modeling the void size function: the linear model, the Shed and Vandenberg model, and the volume conserving model, which differ with each other in the way they deal in the transition from linear to nonlinear regime. Before I introduce the other void statistic, the correlation function, I need to introduce first a very important concept that is present in all large-scale structure studies, the concept of spatial distortions. So here at the left, you can see the matter distribution in a numerical simulation. And let us assume that an hypothetical observer is located here at the center. So now look at the central map. This is what the observer actually sees. The observer sees a distorted distribution of the galaxies. This effect is known as redshift space distortions, and it is a dynamical effect caused by the peculiar velocities of the galaxies that introduce an additional component or contribution to the cosmological redshift that we measure due to the Hubble flow. So keep in mind that we infer distances from redshifts, and redshifts are contaminated by this contribution from peculiar velocities. So we obtain a biased estimation of distances. And as a product, we observe a distorted distribution of tracers. But this is not the complete story. We have another type of spatial distortions, the so-called Alko-Paczynski distortions. It is a geometrical effect when we select a fiducial cosmology in order to transform the observables that we obtain from a survey, namely angles and redshifts, into a physical distance scale. So if we choose a bad cosmology, a bad cosmological parameters, then we obtain, again, a distorted spatial distribution of our tracers. Of course, in observations, both effects appear coupled and indistinguishable a priori. Okay, so now the other void statistic, the void galaxy cross-correlation function. Mathematically, it quantifies the excess probability of finding void galaxy pairs with respect to a homogeneous distribution of such pairs. So physically, the void galaxy correlation function characterizes the density fluctuation field around voids. According to the cosmological principle, the correlation function should be represented in a simple way as a one-dimensional profile, radial profile, with respect to the void center. But this is only valid in real space. In Redshift space, when we deal with observations, this spherical symmetry breaks into a cylindrical symmetry due to the presence of dynamical and geometrical distortions. So instead of representing the correlation function as a one-dimensional profile, it is better to represent the correlation function as a two-dimensional contour map with axes along and perpendicular to the line of sight. So in these maps, we detect some prominent anisotropic patterns. They are a clear evidence of the presence of dynamical and geometrical distortions. So analyzing and quantifying these patterns provides us valuable dynamical and cosmological information. In this way, we can make cosmological tests with the correlation function, with voids. So here you can see the main ingredients necessary to model the correlation function. We need prescriptions for the density profile and the velocity profile in real space, and also a physical description for the Alko-Paczynski distortions and the Redshift space distortions. In particular, for the latter, there are two main approaches, the linear Kaiser model, but applied to the case of voids, and the Gaussian streaming model that is a quasi-linear approach. Okay, so I'm going to explain now the main characteristics of my first project during my PhD. Here we tried to investigate the possibility of improving the way in which we obtain information about distortions from the correlation maps. So we developed the projected correlations method. They are basically two perpendicular projections from these correlations maps towards both axes. Specifically, projecting the correlation function towards the plane of the sky axis, we get the plane of the sky correlation function that is simply a one-dimensional profile that depends only on the angular coordinate. And in a similar way, if we project the correlation function towards the line of sight axis, we get the line of sight correlation function that it is simply a one-dimensional profile that depends only on the redshift coordinate. So here you can see two examples of with the Millennium, the Millennium simulation data. And you can see different measurements with different projection ranges in both directions. So our method provides three novel aspects. The first one is that it is a fiducial cosmology free test because we treat correlations directly in terms of void-centric angles and redshifts without the need to assume a distance scale. The second aspect is that the combination of working on this observable space and using two perpendicular projections of the correlation function allows us to effectively break any possible degeneracy between the parameters involved in models due to dynamical and geometrical distortions. And finally, the third aspect is the covariance matrices associated with the method. They have very positive aspects in the likelihood analysis. For instance, they have a notably reduced dimension compared to the traditional way in which we use the correlation maps. Here, as we have two profiles, then the covariance matrices associated have a notably reduced dimension. So it is numerically more stable when inverting, needed in the likelihood exploration. This allows us to reduce the propagation of errors in the constraining of the parameters. And finally, this is one of the most important results, is that we can use a much less number of mock catalogs. Okay, this slide is just to show you that we have calibrated this method with a numerical simulation, and we are getting some very promising results. But now, the third part, I have to talk about a big problem that we have. So up to here, I presented cosmic voids as extremely nice cosmological proofs. So In reality, I showed you this phase of cosmic voids, but for the last part of my talk, I'm going to present the other phase of cosmic voids. The truth is that we found important obstacles and problems when trying to apply our test to real data, to observations. Basically, the theoretical models couldn't fit the data, and we obtained biased cosmological constraints. But even more important is the fact that all the void community were facing the same problem, not only us. So the origin of the problem is that our standard picture of distortions around voids is incomplete. So traditionally, we have only focused on the spatial distribution of the galaxies around voids. But the truth is that dynamical and geometrical distortions also affect the first step, the previous step, the void finding mechanism. So dynamical and geometrical distortions affect intrinsic global properties of voids, such as their number distribution, size, and spatial distribution. This generates additional anisotropic patterns on observations that leads to biased cosmological constraints if they are not taken into account properly. So basically, the problem is that we identify voids here and not here. Okay, this is our approach to tackle this problematic. Using our spherical void finder, we tried to find a physical connection between the identification of voids in real space, free of distortions, and the identification of voids in Redshift space, fully affected of distortions. This was not trivial to do because the case of galaxies is very different to the case of voids. Galaxies, on the one hand, can be considered as particles. So under this mapping from real space to Redshift space, galaxies are totally conserved. Only their position changes. But the case of voids is very different, mainly because they are extensive regions. So under this mapping from real space to Redshift space, some void can be destroyed, whereas other artificial voids can be created. So it is not trivial to answer the question if both population of voids in real space and in Redshift space are really the same. Okay, so this is one of the most important slides in my presentation because here I'm going to summarize the main results that we found. I'm going to do it schematically because of time, but you can ask me later if you want the technicalities. So I think this figure can help to get an idea of what is happening. Here I show you the distribution of the galaxies in a numerical simulation with those voids identified in real space in blue and those voids in Redshift space in red. So here we have a generic spherical void in real space as provided by our spherical void finder. Okay, so the main results are the following. First, those voids above the shot noise level are almost conserved under this mapping from real to Redshift space. So it is valid to assume void number conservation. This is a very important aspect because this is an important hypothesis in all distortions models for voids. Okay, so the second result is that under this mapping, voids expand. And this expansion effect is a consequence of the classical dynamical distortions induced by tracer dynamics at scales near the void radius. So as you can see here, in Redshift space, a void appears elongated along the line of sight. However, our void finder identifies spheres instead of ellipsoids. So what we get actually is an expanded sphere in Redshift space. So the next result is that void centers are systematically shifted along the line of sight. And this can be understood if we consider a void as a whole entity moving coherently through space with a net velocity. So this off-centering effect is a consequence of a different class of dynamical distortions induced at larger scales due to the global void dynamics. Okay, this is not the complete story. We must also consider the Alko-Paczynski effect on the dimensions of the void. Unlike the expansion effect, the AP effect on the volume of voids can manifest as an overall expansion or contraction. It all depends on the fiducial cosmology chosen. Moreover, we found that all these effects can be treated separately. They are independent effects. And finally, this is valid for the correlation function mainly. We found an additional source of distortion that is the intrinsic ellipticity of voids in real space. So this is considering voids as spherical regions is a first approximation, but if we want to do to measure with precision, we must consider the intrinsic ellipticity of voids.
So, question.
Yes.
Isn't the intrinsic ellipticity correlated with the offset rate?
No. No, it is kind of a selection effect. It's a bit long to explain. I can explain it at the end. But when you select a void sample in Redshift space, when you do this connection between real and Redshift space, and you see those voids selected in Redshift space, in real space, you see a selection effect that very elongated voids, but in real space, not due to distortions, induce this additional effect. Okay, so we provided a complete theoretical framework in order to describe these effects based on physical and dynamical considerations. The important thing here is that this framework depends on the cosmological parameters. So this formulation must be incorporated in current models for the void size function and the void galaxy correlation function in order to obtain unbiased cosmological constraints. And of course, we also provided a statistical framework to prove these effects with the help of a numerical simulation. So I think this picture is funny because it illustrates quite well what is happening with voids. And to finish my presentation, I'm going to explain just briefly the impact that these new effects have on the cosmological statistics. Here you can see the void size function measured with data from a numerical simulation. You can see 4 curves here, but all these curves correspond to the same data set. The difference is that, for instance, the blue curve is obtained in real space without the effect of distortions, and the other 3 mimic possible observational measurements. What I want to highlight with this picture is that the difference between all of them is very significant. So it is very important to consider a complete description of distortions around voids in order to model properly the void size function. And finally, here you can see the projected correlation functions measured with data from the baryonic oscillation spectroscopic survey. And from this plot, I want to highlight 2 aspects. The first one is that the line of sight projection, here represented in red, is very sensitive to distortions. And the huge differences you can see here with respect to the other projection can be accounted for considering all the effects that I just explained. And the other aspect I want to highlight is that with modern surveys, we can measure the projected correlation functions with a high signal. So I finish my presentation with my conclusions. Cosmic voids are promising cosmological proofs for testing the dark energy problem and alternative gravity theories. However, our standard picture of distortions is incomplete. Traditionally, we have focused only on the spatial distribution of galaxies, but we forgot to consider global properties of voids, such as their number distribution, their size, and spatial distribution. This generates additional anisotropic patterns on measurements that leads to biased cosmological constraints if they are not taken into account properly. So in this sense, we provided a complete theoretical and statistical framework to describe these effects. And we also presented I also presented a new cosmological test based on the correlation function that provides 3 novel aspects. First, that we use 2 perpendicular projections of the correlation function that allows us to improve the way in which we gain information about distortions from correlation maps. Second, it is a fiducial free test because we use angles and redshift without assuming a priori a distance scale. It is all contained in models, the transformation. And finally, the covariance matrices associated with the method have positive aspects in the likelihood analysis. Finally, the redshift space effects in voids are detected with high signal with modern surveys. So thank you very much.
Questions?
So a comment and a question. So those redshift space effects are good news, right? Because we have further cosmological information that you can extract from
Yes.
data. So regarding this void size function, is it universal? How? Because I'm familiar with the Hello mass function. I know that it's not universal to high precision, so you need to do a lot of work to that. How is the status?
Yes, the void size function, of course, depends on the tracers you use. More diluted tracers, you will get a different amplitude depending on the sparsity of tracers. But what is important here is that, the blue one that is measured in real space can be modeled quite well with excursion set theory. So if you only use the excursion set theory, you will not be able to fit correctly the curves because, as you can see here, the differences are huge due to distortion. So this is the main, the main idea that we want to transmit. I can show you one of an extra slide. Wait a second. So if you use our theoretical description to correct void size function, you can correct quite well a void size function, and then you can use the excursion set, and it works quite well for constraining the parameters from the excursion set, involved in the excursion set. But in this description here, when you go from here, from here to here, you also have more information about the parameters also.
Maybe I can ask the question with that figure there. So of the 5 effects that you listed, surely there's a hierarchy. And from this plot, it seems that alcohol-Pachinsis is by far the dominant effect.
Yes, but I think when you use a fiducial cosmology, you choose a cosmology that is quite well. Perhaps here we exaggerated the values of the parameters, but I think the dynamical distortions, the redshift space distortions, the red one is the more important.
The redshift space distortions.
Yes. So I have the hierarchy you mentioned here.
Yeah.
Sorry. Here. Fortunately, the void size function is only affected by 2 of the 4 main effects, but the correlation function is fully affected by distortion. So you can gain a lot of information if you model properly the correlation function, physical information, not only about cosmology, but also about the dynamics of cosmic voids and the large scale structure.
Okay, yeah, so let me see if I can understand this. So in some way, you're still assuming that you have spherical voids. You're just mapping that spherical voids to something else according to some model, to some effects. But
yeah.
Still, fundamentally, you assume that in real space, they would have to be spherical.
Yes, but I think the term spherical is just for...
It's just the way that you look for them. You look through the spherical underdensity.
Yes. What is important here is not the sphericity. It's just to locate correctly the center. In real space, if you locate correctly the center, you will see an isotropic outflow. So that is physically important. And for the correlation function, you don't care really the radius. You only want to have is well located the center. So because you measure distances from the center to another galaxy. And from the void size function, yes, it is important the radius, but to do this histogram. And the excursion set theory applied to voids, you need to take spherical voids to fit as the excursion set is written up to now.
Okay, so if there are no further questions, I'd like to thank Carlos again.
Thank you.
We now have Iara.
So I can take my computer later. Okay.
Okay. So first of all, I'd like to thank you all for coming here to watch my presentation. I also would like to thank the committee that read my thesis and evaluated all the thesis, and the organizer for inviting me for presenting my PhD. So I did my PhD in the Federal University of ABC. This university, if you don't know, it's here in the metropolitan region of São Paulo, in the ABC region. That's why it's called ABC. And it's a new university. It was built in 2006. And my advisor was Cecilia Quirente. So I'll talk about my thesis, which I titled Black Hole Spectroscopy, Prospect for Testing the Nature of Black Holes with Gravitational Waves Observations. So just to give a brief overview of what gravitational waves are, I know there was already 2 talks about it, and there will be tomorrow more talks about it, so I'll be brief. So it's old news that gravitational waves were detected in 2015 by the LIGO collaboration. And for this, they awarded a Nobel Prize. And here in this plot, I'm showing the first detection. So it's a detection of a binary black hole merger. We can clearly see here the power spectrum. So it was a very strong detection. So these are for the 2 detectors, 2 LIGO detectors. And with these new observations that are done by these detectors, we can do analyze a lot of new things because we're now detecting gravitational wave strain. So the direct information from the source, and this opens a new field in physics, which we call gravitational wave astronomy. Just a brief overview about the detectors that are operating today. We have 4 detectors operating. 2 are the LIGO detectors, so 1 in the USA. Then we have the Italian detector, which is Virgo, and the Japanese detector, Kagra. There's also a German detector, GO600, but this detector is not sensitive enough to detect gravitational waves. So, and the detections of gravitational waves are divided in observing runs, because in each observing runs, the detectors stop detecting, and they develop better technology, so they become more sensitive. They can detect more things. So in the first observation run, there's only the 2 LIGO detectors. Then Virgo joined the collaboration in the second run, and Kagra recently joined in the third one. So there's a huge gap here. That's because of the COVID pandemic. But the 4th run should start next year. And they also plan for the 5th observation run. There's also a plan to build another LIGO detector in India. So there's a plan, but it's not built already. Just a brief review about the detections that were made. All of the detections come from a compact binary system. Most of them are binary black holes. There are 2 binary neutron stars. And there are 5 events that are compatible with binary black hole merger or neutron star and black hole merger. The neutron star can be a neutron star due to the mass of one of the objects. So we can see here in this plot in the left that for each observation run, the number of observations increase. So in the first one, we have just 3 observations, then we had 10 in the second one. In the third one, we have a lot of observations. And we expect to have even more in the next observations. So we also see that most of detections are black hole detections. These are because they are more massive and they are in the range of the detector sensitivity. And this is good because this is what I'm most interested in. So just to talk a little bit about the waveform emitted by a binary black hole merger. The waveform encodes the dynamical evolution of the binary. So when the 2 black holes are orbiting each other, they lose the energy in the form of gravitational wave. So in this phase, we call the spiral. So the frequency of the gravitational waves increases over time. So also the amplitude increases over time. Then the 2 black holes merge into each other. And the remnant black hole emits gravitational waves, and the oscillation ceases. The part of the gravitational wave I'm mostly interested in is the ring down, which is the last part. This part is very interesting because you can approximate it with quasi-normal modes. Quasi-normal modes are solution of the black hole perturbation theory. So you have you perturb a black hole, you have a solution, and we found out from simulations that we can approximate the ring down part of the waveform with perturbation theory. So why do we call quasi-normal modes? We know very much about the normal modes. The normal modes are defined in closed systems, so we can define the boundary conditions to vanish at the boundary. So when we set these boundary conditions, this vanishing in the boundary, we get that the solution of the waveform will have a constant oscillation, so they will look like normal modes. But when we have a black hole, the black hole makes the system open, and we also have the universe, which is also open. So the system is opened in both sides of our system. So we cannot set an arbitrary position where the waveform will vanish. We cannot set a boundary. So the conditions we set is that no waveform comes outside the black hole. That's a physical condition. And no waveform is coming from infinity, so we don't keep perturbing the black hole. We want a solution of a single perturbation. And when we set these conditions, we get that the frequency of the solution, the wave solution, are complex. This means that we're going to have an exponentially damped wave. So in this solution are the quasi-normal modes. And the most important part of the quasi-normal modes are the frequencies. We can divide the frequency omega here into the oscillation frequency and the damping time. This frequency, the important thing about these frequencies is that they depend only on the properties of the black hole. So we know from the no-hair theorems that a black hole is described just by 3 numbers, the mass, the spin, and the charge. But for astrophysical black holes, we consider that the black holes are neutral, so we just have the mass and the spins. So this means that if we know the mass and the spin of the black hole, we know what are the frequencies of the quasi-normal mode frequencies of this black hole. No matter how you perturb the black hole, these frequencies will be always the same, the frequency of oscillation and the damping time. On the other hand, if you measure the frequency, you can know what are the mass and the spin of the black hole. So this quasi-normal modes, as I told you before, it was seen in simulations that the ring null part of the binary black hole merger is well approximated by quasi-normal modes. And in the first detection already, they looked for a quasi-normal mode, and they found the dominant quasi-normal mode, which is the fundamental quadrupolar mode, the 2-2-0 mode. So how did they do that? They analyzed the waveform after the peak of amplitude, because the peak is approximately the time of the merger. It's not known. They started to analyze the waveform after this peak of amplitude, and they looked for the frequency of oscillation and damping time. So here in the x-axis is the frequency and the damping time. And they found out that 3 microseconds after the peak, the results for the frequency and damping time are compatible with the results they get when they analyze the whole waveform. So when you analyze the whole waveform, you get a final mass and spin for the black hole, you know, from simulations. And when you compare this analysis with just the ring down analysis, you find a compatible frequency and damping time. So this is a consistent test. We say we detected the fundamental cos-normal mode because we compared with the rest of the waveform. This was done also in other detections, not just the first one. But the first one was good because it was a really strong detection, and we could see the ring down. You can't see the ring down in all of the detections. But this kind of analysis, we say that it's a consistent test because it depends on the rest of the waveform. If we want to look just on the ring down, we can do something that it's called black hole spectroscopy. This was proposed in 2004. And we know that the quasi-normal mode's frequencies depends only on the properties of the black hole. So if we detect the dominant mode, we know we can compute the mass and the spin. But if we detect another mode, we could also compute the mass and the spin. So detecting 2 modes, we can check the consistency between them. So this is an independent test because it only depends on the ring down and checks if the matrix is described by the Kerr matrix. Because if it's not a black hole, a Kerr black hole, this frequency, you will detect another frequencies. For example, we can detect a frequency for the 2-2 mode that looks like a Kerr black hole, then you detect another mode, and you don't find a consistency between these modes. Because the mode all the modes define the mass and the spin of the black hole. So there are 2 kinds of subdominant modes. The first kind are the higher harmonics, fundamental modes. So we call fundamental modes the modes that have longer lives, so they take more time to decay. And then the subdominant modes are harmonic modes, so the numbers L and M are not equals to 2. They're not the quadrupolar modes. And when you look in the simulations, the amplitude of these modes, and so here a plot is the ratio of amplitude between the harmonic mode and the dominant mode, you can see that, sorry, for the mass ratio of the binary, for low mass ratio binary, so for initial black holes with very similar masses, these modes have very small amplitudes and they increase with the mass ratio of the binary. So when there's more asymmetry in the masses of the binary. The other kind of subdominant mode are the overtones. So you have the dominant quadrupolar mode. The fundamental mode is the mode that has the longest life. And the overtones decay faster. So they have frequencies very similar to the fundamental mode, but they decay much faster. Sorry. And when you look in the simulations for the amplitude of this mode as a function of the mass ratio, you can see that they are more relevant when the mass ratio is small and less relevant when the mass ratio is high. And you can also see this is not the same scale, that when the mass ratio is high, their amplitude is very near the amplitude of the higher harmonics. Sorry. Sorry for that. So this means that the overtone are more relevant. Oh, sorry. Are more relevant when the mass ratio of the binaries are small. And this is important because most of the LIGO detections have low mass ratio. Here, it's the opposite relation. So 1 equals small mass ratio here, and 0 equals very high mass ratio. But most of the LIGO detections are compatible with equal mass ratio. So we don't expect to see much of the higher harmonics. but the overtone should be relevant. For the subdominant mode, people looked for them in the literature, so in the detections. And when they did it, they modeled the waveform with more modes, and then found out that when you add more modes, you can decrease the errors near the peak of amplitude. But this is, we call it a weak detection of a subdominant mode, because you can add more modes. So when you add one more mode, you add 4 more parameters in your model. So you are not sure if you're really detecting it or just adding more mode and get a better result. So this is not a conclusion for the detection, because the statistical evidence for this kind of detection is very small. We can really say we detected another mode. And when you look, I don't have the plot here, but when you look for the frequencies, you can't really constrain the frequencies of the subdominant mode. So before talking more about it, I have to talk about the future gravitational wave detectors. There are 2 kinds. The first kind are the ground-based detectors. There are 3 of them: the Einstein telescope, which is in Europe, the Cosmic Explorer, which is in the US, and NEMO, which is in Australia. NEMO is going to be more sensitive for neutron stars. And there are also the space-based detectors, which is LISA. It's a European project, but NASA is also in the project, and Tianqing, which is a Chinese project. So here I'm showing the plots of the noise of the detectors. So when the signal of a detection is above this curve, we can say that the signal has been detected. And we can see here that the ground-based detectors detect the high-frequency signals, and the space-based detectors detect the low-frequency signals. So as the mass of the gravitational waves is inversely proportional to the frequency, the space-based detectors will detect supermassive black holes. So even though the noise seems to be much larger than the other ones, LISA will be really sensitive, because it will detect supermassive black holes. So to talk about the detectability of the modes, we propose a more conservative criteria, because we want to look for statistical evidence for a second mode. The first criteria was proposed by Bergmann in 2006. This is a generalization of the Rayleigh criteria. So the Rayleigh criteria was proposed to distinguish 2 bright stars very near each other in the sky. So this criteria says that you detected a mode if the difference in their frequencies is larger than the maximum error uncertainty of the estimated frequency. So you have to have, it's like this plot here. So if the uncertainty is very large, you cannot distinguish the frequencies. And the same thing for the jumping time. So we can see that this criteria poses different constraints for different subdominant modes, because the harmonic modes have very different frequency from the dominant mode, but their damping time are very similar. On the other hand, the overtone have very similar frequency, but very different damping time. So each of these inequality will constrain modes differently. This criteria is very restrictive. So if you can satisfy this criteria, you have a very large statistical evidence. But we can go a bit less restrictive and do model selection using Bayes factors. So we consider that we can say that a second mode has been detected if the logarithm of the Bayes factor between a model that contains two modes, so the dominant mode plus the subdominant mode over the model that contains just the dominant mode is greater than 8. So this is also very conservative, but it's much less conservative than the Rayleigh criteria. And here, just a plot to check that this threshold is high enough, because we computed the Bayes factor of a signal containing just the dominant mode, and checked that none of the signals returned a Bayes factor larger than 4 here. Yes? Okay. Using both these criteria, we compute what we call the black hole spectroscopy horizons, which is the maximum distance we average over sky and all the angles, that a second mode can be detected using the Rayleigh criteria or the Bayes factor criteria. The first thing we can see is that the trains of the curves are very similar. So no matter which criteria you choose, you get the same train. For low mass ratio binaries, you get that the overtone is easier to detect than the higher harmonics. And for high mass ratio binaries, we get a preference for higher harmonics. In the Bayes factor, we get a better preference. But still, you have the same trains between the cases. And we can see also that for the Rayleigh criteria, even the third generation detectors won't be sensitive enough to detect a second mode using the Rayleigh criteria for most of the current detector, the detection that already happened. And for the Bayes factor criteria, the third generation detectors will be good enough. I have the LISA curve here. You can see that this distance is very large, so LISA will detect almost anything. So just to check, to make this more general, we construct a signal containing all the most relevant subdominant modes and checked for we did model selection with a model containing one mode, a model containing two modes. Now we don't specify which is the second mode, and a model containing 3 modes. And here are the results for the black hole spectroscopy horizon. And we can see that the model contains 2 modes with a signal containing all the subdominant modes is compatible with the largest horizon here for the case containing just 1 mode. So we can shows that the analysis with just 2 modes is good enough. I'll just skip this. Just show that we recovered the parameters of the largest horizon. And in this last plot, I'm showing the estimation of the parameters, the black hole parameters, the final spin and the final mass, using the ring down only for the detections. So when we are outside the horizon, we have the model that contain 1 mode or 2 modes to recover correctly the results, but the subdominant mode is highly uninformative. When we are on the horizon, we can see that the model that contains just 1 mode gives biased results, so wrong results. So we need the 2 modes to model correctly the signal when we are at the horizon distance. When we are at the horizon of the Rayleigh criteria, this is pretty clear that we need another mode, just get a better result with less uncertainty. I'll just stop here. Thank you.
Questions?
Very nice work and very nice presentation. Thanks.
Thank you.
I have a slightly technical question. Where do you start the ring down? How far after the
yes.
merge do you start the ring down?
We start 10 m mass after the peak. We're not starting at the peak at 10 m. 10 m would be the time where the fundamental mode was compatible in the detection. This 3 microseconds is 10 m after the peak.
And how high in L and N can you go before, where you still have something after this? I mean, there would be higher modes which die before you reach 10 m, right?
I'm sorry?
If you go to high enough L and N, which die very fast, some of them wouldn't even survive to...
Yeah, I didn't look. You mean the L overtones for the L
yeah,
and
the
M?
overtones and also the higher harmonics.
Yeah, the higher harmonics, the fundamental higher harmonics. Yeah, I didn't. I looked for just for these 3 ones because the other ones have very low amplitude. If you look at the simulation, they are separable in the simulations. If you look at the simulations, they're not really. They have very low amplitude, so I didn't look for them.
Okay, thanks. This is very nice.
So I have a question. So in your test where you have different modes that you add by hand, how do you adjust the different the initial amplitudes? I mean, are they chosen from the GR simulations, or do you provide? Yeah,
this.
There's a previous slide.
This.
One more.
This.
Yeah, there where you have different modes, right? You have the different these models and the signal. So the amplitudes of each of the modes, are you putting them by hand or?
Yeah, they come. I'm putting by hand because I'm doing all in the Fourier domain. So I'm not using the simulation because I would have the errors from the simulation and taking the Fourier transform of a discrete space. But the amplitudes come from the simulations at 10 m after the peak. Okay. So I just fit in the simulations at 10 m, then we get the amplitudes.
Okay, if no more questions, let's thank Iara again. And now we have Marcos Argañaraz.
It's already okay.
You can just untick.
Thank you. I'm going to use this. This one? Yes, this one. Okay. Sorry. Okay. Wait a second. Yes. Okay. It'll work. Where's the pointer? Okay. Well, to start, I'm very glad of being here giving this talk. Before I start, I would like to thank the ICTP for all the support, and of course, for the special mention in the Gravity Prize. So now I'm going to start with the talk. As you can see the title, the main subject is null coordinates. So to start, I would like to give you some intuition about the meaning of the null coordinates, okay? So I'm going to start with this question. Suppose that we have null coordinates in a certain space-time, usually the outgoing and ingoing null coordinates. What is the meaning of that a null coordinate, for example, the outgoing null coordinate u has a certain value, u equal to constant, u equal to 20, to 10, some value, constant value, okay? To understand this, we can start with the most simple example, that is Minkowski spacetime, where the null coordinates are very well known. Here we have the outgoing null coordinate, and here the ingoing null coordinate. So let's look to the equation 1, and let's try to understand what means u equal to constant. Here we have the speed of light multiplied by t minus r. The only way that this will be constant if we move along a light ray, because we know light travels at the speed of light, okay? So we can choose one light ray where equation 1 is satisfied. So the question is how many other light rays we can take in order to satisfy this equation? Well, there are many others. In fact, we can choose a set of light rays where equation 1 is satisfied, okay? So, which is the intuition I want to give you. When we talk about a null coordinate, implicitly, we are talking about a set of null rays. It means, talk about null coordinates, we talk about this set, and we usually call to this set a null congruence, okay? Well, but with this null coordinate, we want to describe the whole spacetime. So this set of null rays must fill the whole spacetime. One way to do it, for example, in Minkowski spacetime, is to take these outgoing radial null rays. So if we take this set of radial null rays, we can fill the whole spacetime, and therefore we can satisfy this equation in the whole spacetime. And then we will get a null coordinate that describes whole spacetime of Minkowski, okay? So, a final remark. Every time we talk about null coordinates, implicitly we are talking about a null congruence, okay? But this null congruence has to fill the whole spacetime, but also has a very nice property, a geometric property, as you can see here in these blue circles. This has to do with if we take a fixed value of t, we get a sphere, and in that sphere, we have the null rays that are orthogonal to that sphere. If we take another time, or another value of the coordinate t, we get a bigger sphere, but again, the null rays are orthogonal to that sphere, okay? So every time we talk about null coordinates, we have this null congruence with these very nice properties, okay? That's the intuition I want to, in this first slide. So what about more complicated cases? For example, Schwarzschild. The null coordinates in Schwarzschild are well known. They are the Eddington and Wilkinson coordinates. So the first question is, which is the null congruence that is related with the Eddington-Wilkinson coordinates? Well, that null congruence is a well-known, the principal null congruence. There is a geometrical definition for this congruence. This type of congruence has certain properties we can define for Schwarzschild, but also we can define it for Kerr spacetime. The thing is that, similar than Minkowski, this congruence has null rays that goes radially in outgoing or ingoing, but in this way. So we have the null congruence with nice properties. Therefore, we can define the Eddington-Finkelstein null coordinates. But what happened in Kerr? These principal null congruence have twists. What is twist? The null rays twist like this. Which is the problem with that? If the null ray twist, we cannot define a surface in such a way that for each null ray is orthogonal to a surface. But if we take the next null ray, we have to change the surface because this is twist. Therefore, the principal null congruence do not have the nice geometric property that we need to define the null coordinates, okay? So we need another null congruence to define null coordinates in Kerr. Okay, but what happens if tomorrow we go to the textbooks and we try to study this subject? Well, it usually is the Schwarzschild case is presented first. And okay, we have that the principal null congruence has very nice properties, and we can define the null coordinates in the whole spacetime. And because we know the null coordinates in the whole spacetime, we can construct these compactified diagrams, Carter-Penrose diagrams, that represent the whole spacetime. But also in the textbooks, there is present a compactified diagram like this one. The author of this compactified diagram was Brandon Carter in 1968. I think that he knew that principal null congruences have twists. So the only way he managed to define a null coordinate was, okay, principal null congruences have twists. I'm going to elect just one null geodesic, which do not have twists. And that null geodesic is the one that goes along the axis of symmetry. And because it doesn't have twists, you can define a null coordinate here. And here you have the surface which the null geodesic is orthogonal. But this is only valid at the axis of symmetry. So this compactified diagram is hugely incomplete. It's incomplete. It's only valid at one line of Kerr spacetime, okay? So we must always remember that when we see this kind of diagram of Kerr, we have to remember it's only valid at the axis of symmetry, okay? If we see this diagram in the textbooks. So we know that we need a different null congruence to define the null coordinate. So if we look in the literature, what we will find? Well, we will find that this is a very elusive subject. There are many other authors that have tried to define these null coordinates. In fact, for example, there is a Physical Review Letter article here in 2004 that gives this definition of null coordinates, okay? So what is the problem with this? The problem is that all these other attempts to define null coordinates have a problem at the axis of symmetry. I mean, for example, null coordinates are a tool. If you want to use that tool, for example, to solve the scalar field equation, what you will find if you use these null coordinates is that you get a term with a divergence. So you can solve it, that equation, okay? So this is a tool, but when you want to use it, you have to face these divergences behaviors, okay? So this is the first part of the talk. I give the context, the problem, and now I'm going to tell you how we were able to solve this problem and how we were able to make a new definition of null coordinates in Kerr. Well, if we already have intuition, it is very important to get the correct null congruence. So how we find it? We have to start from the scratch, from the beginning, and we hear from this work of Carter, we know that the most general null congruence has this tangent vector. If we take the lower index, we will work with smaller expressions, and for these presentations is very good. And here you can see the most general null congruence. Here E, L, and capital K, which is here, are constants of motion. It means that if you move along one geodesics, E, L, and K remains constant, okay? So if we take different values of these constants, we will be electing different types of congruences, okay? So this is very general. We want to choose the one that works, that has the very nice property. So we make this selection, and we were inspired by the center of mass definition. What is that idea? We take a sphere at infinity, we go to R to infinity, we take a huge sphere, and from all the geodesic, the null congruences, we elect the one that reaches that sphere at infinity reaches orthogonally. I'm trying to schematic describe the idea here, okay? So we have a sphere at infinity, and the null congruence reaches with the null rays orthogonally to that sphere, okay? So if we impose that condition, this imposes a condition over these constants of motion. L must be 0, and capital K, which is the Carter constant, must be a squared sinus square of theta, okay? So, but this is a condition at this sphere at infinity. What happens if we go inwards? Well, we want that the congruence still have this nice property of being orthogonal to these spheres or something like spheres, okay? So mathematically, this condition is traduced imposing that the exterior derivative of the tangent vector of the congruence must be 0. So this is just saying we want that our congruence is hypersurface orthogonal everywhere. So if we impose the condition, this is codified in this differential equation. So if we solve this differential equation, all the details for electing the congruence are codified just here in this differential equation, okay? We did condition at the sphere at infinity, okay? So this is a nonlinear differential equation. It's very difficult to solve analytically, and we did it numerically. And this is a very nice equation. The solution behaves very nice, and we have the solution here at infinity, and we have the solution even inside the event horizon. We can go as far as we want up to the ring singularity. So we can find the solution of K even up to the ring singularity of Kerr. So we can go very inside, and this function behaves very well, okay? So with that solution, now we can go to the congruence that we were electing, and all the information of our election is here in this function K, okay? So the next step is, okay, we have to integrate these equations to define the outgoing null coordinate and the ingoing null coordinates, okay? Well, the angular dependence here, Rs, I mean, if you remember Minkowski, you have U equal to T minus R. The null coordinate in Schwarzschild is T minus the tortoise coordinate, R star. But in Kerr, we have this R that we call spherical, R spherical. And this has a dependence on the angle theta. That's what one expects, because Kerr do not have spherical symmetry, only axial symmetry. So this depends on theta. So these are the final expressions of the null coordinates. And now let's back to the intuition picture, and let's see how these behave. Okay, these are the null coordinates that we have already defined. So which is the null congruence? The null congruence looks like this. Reach orthogonally to a sphere at infinity, but if we go inwards to inward regions, we don't have any more perfect spheres. We have topological spheres. And why I make these draws like this? Because we were able to compute the Gaussian curvature of each of these surfaces. And from the values of the Gaussian curvature, we have an equivalent surface that are oblate spheroids. I mean, if you go to infinity, Rs is a perfect sphere. If you go inside, this sphere is more smaller in this axis than in this axis. It becomes an spheroid, oblate spheroid, sorry. And we know that for the values of the Gaussian curvature, okay? So this is the final description. I hope that this makes connection with intuition. And then we can also define the extended null coordinate that allows to cross the event horizon in the same way that Kruskal null coordinates does in the Schwarzschild case. And here I show you the Kerr metric in these null coordinates. I show you the inverse because it's the shorter one. Okay, so this is the first part of the talk. I give you the context and how we define this null coordinate. And now I'm going to show you an application example. And we will use this coordinate to solve this equation, which is the scalar field equation. Here you can see the equation in Boyer-Lingwitz coordinates, and here in the extended center of mass coordinates. To make a little bit simpler the numerical code, because we solve it numerically, we take axial symmetric initial data. So the differential equation is a little bit simpler, but it keeps a non-trivial angular dependence on theta. So we solve this equation numerically. Here I show you two types of initial data. We call this to Bell type and this to harmonic type. And here I show you the domain. Well, because we are using double null coordinates, the way that you solve this equation is very different than in Boyer-Lingwitz. Here I'm showing you a compactified diagram of Kerr, where here we have region 1, which is outside the event horizon. Here's region 2, is inside the event horizon. And this compactified diagram is valid for all values of theta. This is why? Because we have the null coordinates that are valid in the whole spacetime. It's very different than Carter's. Carter's were only valid at the axis of symmetry. This is valid for all values of theta, okay? So how we solve this equation? We have to give initial data here in order to obtain a well-posed problem. We put here initial data different from 0, and we evolve numerically. And here I show you the evolution. As you can see, Here we have the evolution. It reached the event horizon. Everything is OK. And we can go even inside. So we give initial data outside, and we keep the evolution inside. And we can do the same with the other initial data. We give initial data outside, and as you can see, it behaves very well crossing the event horizon. And we don't have any problem at the axis of symmetry. I mean, this is like an indirect proof that the null coordinates work very well and can be used for any computation you want, okay? And these numerical results can also be shown in this kind of plot. Here, u equal to 0 is the event horizon in null coordinates. And you can see here the scalar field at different angle values. And in u equal to 0, you can see that everything is OK. There is no problem. Null coordinates function well. The numerical code that solves this equation works well. Everything is OK. So to finish, some final remarks. I have to say that this is the first time that the scalar field is solved using double null coordinates in Kerr. You might imagine why is that. Before this work, there wasn't a good definition of null coordinates. So everyone who tried to solve this scalar field had to face the problem of divergences on the axis of symmetry. So I think that's why. The previous work on this subject, solving the scalar field in double null coordinates, was done by Ganlach. He did it in Schwarzschild. So, but now we did it in Kerr, finally, because we have the null coordinates. And we use a second-order precision code. Here, I don't show you the details of the numerical scheme and code because of time, but you can find in the published work, okay? And we have shown that the scalar field is well behaved. We can give initial data outside the event horizon, and you can cross the event horizon without any problem. And also I have to say that we have tested the precision of the numerical solution, and also we have used an independent test of energy conservation, and the energy conservation was very good, less than 0.005%. So the numerical results are very reliable. So this is my contribution of my PhD thesis. I hope that many other colleagues start using this new tool to study Kerr spacetime. So that's all of my talk. Thank you for listening.
Questions?
Thank you for the nice presentation. So as you were presenting, I was trying to intuitively connect your work to null geodesics. For instance, there's a slide you showed the condition of the constants of motion.
Here?
Yeah, this one. So L is like related to the angular momentum,
yes.
Maybe. So I understand that when it's 0, if it's a geodesic, they're just the only special type of geodesics that can reach the North Pole and the South Pole. So does this condition imply that this work can only work for polar null geodesics, the geodesics which can only pass through the poles using this condition? I don't know if that makes sense.
Okay, maybe it is also related. In fact, if one studies this in more detail, at the end of the day, the congruence that we construct is a very particular one. It is a congruence where each of the null rays has a different value of k. This is why we have to solve the k equation. But we also have this null geodesic that goes through the poles. So maybe this can be related with that L is equal to 0. But the other constant of motion, k, make that the other null rays behave like this. So there is a combination of constants of motion, as you can see.
Okay. So because k is not 0, that implies like the equatorial null geodesics cannot cannot work? Because I think when it's
Well,
0, they're equatorial.
Well, the function k is like this one. And you can see here you have theta equal to 0 equal to p. And you can see that the k is 0 at theta equal to 0.
Yeah.
And 0 and p.
K is 0 at theta 0.
Eh? I'm sorry.
K is 0 at theta 0. I thought it would be 0 at 1.5.
Also is 0 here.
Okay. Okay. Thank you.
So k is 0 at the axis of symmetry and the equator.
Thanks for the talk. I thought it was very interesting. Just so that I can understand, was there any special procedure that you had to do? I mean, these double null coordinates allow you to do evolution inside the horizon without having to do excision or smoothing the metric in some way, right? So, I mean, just to clarify, yeah.
That's right. Because that's a property, that is the expected property. For example, in the Schwarzschild case, the Kruskal null coordinates allow to do that. And here we have the extended center of mass null coordinate that do the same, but in Kerr.
Okay, that's very interesting. Thank you.
So I have one question. So as you mentioned, and this is related to probably also the last one. So in a sense, yeah, you're going into the black hole and you're excising because you stop the evolution at some point, which is fine. So this is a very nice setup to study, say, the context of mass inflation inside of the rotating black hole spacetime. But on that, so part of the reason that the Tarkovsky equation is very popular is because then you can do separation of variables and then treat the angular and the radial part separately. Do you know with your coordinates where this stands, or separability goes out the window? Given that k now, given that k is known numerically, that probably is tough to decide at the moment.
Well, we have this differential equation. We didn't try to do that, to do something like separate the equation in different, the dependence on different coordinates, like many others do in Tarkovsky. We simply have this differential equation. We solve it full numerically. That was our approach up to now. We didn't study to try to make a variable separation for trying to solve this differential equation. We solve it just numerically.
Okay, so I think Carlo again. Marcos. Sorry, Marcos, my bad. And the final talk is Caroline.
I just put it.
You're using this laptop?
Yes, sure. Can I try to log into my email so I can open with the Google? Is that all right?
If you want to, yes.
Okay.
So I want.
Is this one right?
There is a wallet here.
Okay, so because I updated. Just sorry.
Sure.
Me.
I just don't connect now, so people won't see your password, which is the same as your bank account, right?
Let me. Okay, 1 second. Oh. Okay. Yeah.
Sì, no, vuoi evitare di collocare intanto che apri il mio email privato. Agora posso collocare.
Which is
I think it's running low batteries.
right. Trying to see if I can escape this. Okay, so hello, I'm Carol. Currently, I'm a postdoc at the Queen Mary University of London, But what I'm going to talk to you here about is the work that I did during my PhD, which was supervised by Raul Abramo, who's here. Before I start, I would like to thank the organizers of this event and the ICTP-SAIFR for giving this very nice prize for us. It's an honor to be here talking at this stage because it's ICTP here. This building is like my third home, so it's very nice to be finally giving a talk here. Okay, so I was going to start by talking, trying to motivate why to use large-scale structure, but I think that it needs no introduction given the crowd that we have here. And so I'm just going to use these slides as a sort of motivating and giving you a rough idea of the two topics that I'm going to discuss. Basically, with the large-scale structure, the interesting thing is that we have a huge volume of the universe that we can map if you compare it with the almost two-dimensional maps that you can have from the CMB. This is a lot of volume. And with more volume, we can sample more modes, and we can sample larger modes in a better way than if you are stuck with a small volume of the universe. So this gives us a nice way of doing statistics. And when we go to the larger scale, so if we can sample these larger modes in a better way, this means that we can go to larger scales where some very interesting effects start to appear in the distribution of large scale of dark matter tracers. One example, Raul briefly mentioned in his talk, is the non-Gaussian initial conditions of the universe, which leaves a very specific imprint on the bias of dark matter tracers. So if you break the Gaussian assumption using a specific kind of non-Gaussianity, what you have is that as you go to larger scales, as you're going to low wave modes, it means that you start to have some scale-dependent features on the bias of your dark matter tracers, for example, galaxies or dark matter halos. And this can be observed at the very large scales that you can measure. And this is something that is interesting to use the large-scale structure to do. And also at the larger scales, when we start to look at these effects, starting to analyze these very small K modes, what happens is that it is important to notice that the observations that we make in cosmology are done in our past light cones. So we are not stuck with a box that every point is in the same hypersurface of constant time, but what we are actually observing is the structures as we see them on our past light cones. So this thing here will put imprints on these larger scales, and it is impossible, and it is very necessary to model these things if we want to properly understand theoretically what's happening with the dark matter distribution at the largest scales. And finally, with the large-scale structure, we can have a hint on nonlinear physics. We can go from a very smooth, initially almost Gaussian distribution, and as you turn on gravity, then what's going to happen is that these structures, which were very close to a Gaussian field, starts to collapse and form highly nonlinear structures. And this thing is not something that you can just discard. This is a very interesting thing because it will give us extra information about the distribution of dark matter on tons of scales. And also hints on the theory of gravity, for example. So I'm going to talk about a bit of those past light cone effects that we have on the distribution of galaxies and how we can use this nonlinear evolution of the gravitational field in order to improve photometric redshifts in a galaxy survey. So for the general considerations, what I would like just to make a brief recap, also Raul mentioned this in his talk. Thank you, Raul, for doing it. So if we want to understand the large-scale distribution of dark matter, we can compute the one of the cosmologist's preferable quantities, which is the density contrast, which is just the density that you have at some point, some x, y, z coordinate at some fixed time. You can subtract the spatial mean of that, and you can construct what is your density contrast. This gives you, you can use perturbation theory to understand how this thing is going to behave. And you can also think about when you're going to look at dark matter, what we are actually looking at, for example, is galaxies or dark matter tracers. And to do that, we compute the number counts. So we count how many galaxies we have in a pixel, for example. and we subtract the angle average of that of these, and then we can build a sort of density contrast, but now instead of a continuous density field, we use the number counts of galaxies. And the point is that different galaxies, for example, a blue galaxy or a red galaxy, as Raul mentioned, they are different tracers. They are going to trace differently the distribution of dark matter in the universe. And what this means is that when you compute, for example, your two-point statistics, so this is the Fourier transform of the two-point correlation function, the power spectrum here, what you're going to have is the presence of, for example, a linear bias, which can have different values for different tracers. And also, in the presence of those non-Gaussian initial conditions, what you could have is a k-dependence inside this object. So this is something that you need in order to properly understand how these different galaxies or dark matter halos will be tracing your dark matter field. So one example, and this is a slice of a light cone built from the relativistic n-bodied simulation devolution. So this simulation involves the Einstein field equations in the weak field limit, and gives you, it's an n-body code, and gives you, for example, as an output, the light cone containing, for example, dark matter halos. And this is a tracer that I'm going to use in the first part of my talk. So in this simulation, we have a light cone. So in the z direction here, which this is the Cartesian coordinate, but you can associate this as you were looking at as redshift here. So different points here are at different redshifts inside the simulation. And this is just a slice through through the y direction. And this is an example of how different halos, so each different color here is a different type of halo with a different mass, have very different linear biases. So this is what is meant, that B alpha is going to have different values, it's going to trace the dark matter field differently. And we're going to use these halos here just for the purpose of the next, of this talk. So another interesting thing to do is that, okay, when you look at here, this is your Cartesian coordinates, for example, at some fixed time. But what we actually observe is some angles in the sky, so theta phi, and some redshift that you measure from some galaxy survey. And this is a credit from Camille's Bonvin talk. But what happens is that if you have a perfect three-dimensional Robertson-Walker universe, which is unperturbed, then the photons emitted by a source would follow a straight path until reaching us here, the observers at our detectors. And then it would be a very straightforward thing to compute what is the x, y, and z coordinate of the source, because you know exactly that this photon followed this path here. However, in the universe, we have tons of stuff between the source and the observer. We have matter in the middle that is lensing the source. So, for example, what happens is that the source here, which emitted a photon, the photon was distorted throughout its path until hitting us here. And then when we look at this object with the angle and the redshift that we measured, we can actually place the source in a different location than what it really is in reality. So this gives rise to distortions in how we model theoretically the number counts that we measure. One particular example of this is redshift space distortions. So this is a distortion in energy of the photons. This that I'm showcasing here is just the Kaiser effect. So if you have the observer here looking along this line of sight, and you have three galaxies, okay? So the fact that this galaxy has an inward velocity here following towards this other galaxy, and the galaxy 2 have a velocity in the opposite direction. When you project this thing along your line of sight, what you're going to see is a squashing in your two-point correlation function. It has been shown in many talks here, in particular, Raul also showed this. If you start entering the nonlinear regime, you start to see the fingers of God here. This is just showing the linear case. So basically, the fact that you have a velocity which you're projecting along the line of sight will add on top of the redshift that you would have from a pure three-dimensional Robertson-Walker spacetime. So this is a shift in coordinates, and this must be accounted for. One thing that I would like to call your attention is that this thing is symmetric along the line of sight. So if you look this way, it's going to be exactly the same picture. It is completely symmetric when you look at the parallel direction. So this brings me to the distortions that I studied in my PhD, which is these relativistic features in the clustering of dark matter halos. And I like to show this picture because I think this is very intuitive to summarize the kind of effect that I was looking for in this work, which is basically now if you think about this as a gravitational potential, and you have a bright galaxy here at the bottom of the potential, in order for us here at the observer to observe these galaxies, they have to emit photons, and these photons have to climb out of the gravitational potential. So if these two galaxies here that I'm calling faint, so these are two different types of galaxies, will emit photons that will have to climb a certain amount of gravitational potential in order to escape and reach us here. So these two galaxies will suffer a particular redshift here, and they will be, instead of located here, we will think that they are actually at these positions, while the bright galaxy in the very bottom of the potential the photon emitted by it will have to climb a much higher steep in order to escape and reach us. So this galaxy suffers a larger gravitational redshift than the other two galaxies. And if you put this against the line of sight, you're going to see that a situation which was originally symmetric, so these galaxies were exactly at the same distance from the bright galaxy, now they will exhibit an asymmetry along the line of sight. So something that was initially symmetric now becomes asymmetric. And this thing will introduce a dipole. So this is here is just to show the theoretical expression for the number counts of galaxies at any dark matter tracer as you observe at a certain angle and redshift. And particular, this one here is the effect that I just give you as an example. This would be the effect of the gravitational potential, redshifting the photons. Then you have here the standard Kaiser effect, which is just the redshift space distortion, traditional effect. And here you have effect of magnification bias, which is associated with lensing. And the interesting thing is that if you look at this expression, these three terms here, they cancel if you are assuming the equivalence principle, meaning that this kind of full expression, the full thing that we have in general relativity can actually give us a clue on, for example, if the equivalence principle is holding or not. And this has been studied by Camille Bonvin and her group in Geneva, how you can use this to test this assumption for dark matter particles. So I'm going to, in this work, we focused only on the projection along the line of sight, and why so this is the main quantity that we are working with, given its expression. We are neglecting the integrated terms and the things that depend, that does not depend on the projection of the velocity along the line of sight. And if you do that, if you consider only these terms, and you Fourier transform your overdensity of your number counts, you can compute the Fourier two-point correlation function of the power spectrum when you cross-correlate different types of galaxies. So that I showed two faint galaxies and a bright galaxy, which could be alpha and beta, so two different objects that trace differently the dark matter distribution. And when you compute it, you see that this expression appears, and this thing here is proportional to the projection along the line of sight. So you can use the Legendre decomposition to extract its moments. So in this particular work, we tried to see if we could find this dipole in the power spectrum of redshift space dark matter halos from the devolution simulation. And one interesting thing to look here is that this depends on this parameter A alpha. A alpha is carrying information from your tracer, such as magnification bias, evolution bias, and quantities that are actually important when you try to model the large-scale structure, because these things here encode the evolution of your tracers throughout the redshift. So it is important if you're trying to do analysis in the past light cone. B alpha here is just the linear bias of the tracers, and F is the growth rate of structure. As a result, we unfortunately could not claim a detection. We can, so solid here is the predictions that we have for the dipole. And the points here is the things that I managed to extract from the simulations by estimating this dipole directly from those dark matter halos. The important thing to keep in mind here is that we had a light cone simulation. We managed to take the halos, to construct the halo catalog, and to develop the pipeline to try and measure this effect. The problem was that the simulation was not big enough, and we could not claim the detection. But now we have a pipeline, and we have a larger understanding on how to do that, maybe with larger simulations, and maybe even apply that thing to data. So I'm going to skip now to a very different subject in the remaining of my talk, which is something that I did with these people here. This was actually an idea of Davi Alonso, and we developed this in the last year of my PhD, which is using the bispectrum now, not the power spectrum, but the bispectrum between galaxies and intensity mapping, in order to improve the measurements of photometric redshift. So I'm going to explain this a bit better. So when it comes to analyzing the large-scale distribution of dark matter with discrete tracers such as galaxies, dark matter halos, or quasars, for example, we are trying to sample very large volumes of the universe with these discrete tracers. And one of the things is that we have to overcome shot noise. So if we want to have enough objects in order to detect these effects that will appear on the very large scales of the universe, we need very dense samples. And as Antonino showed in his talk about Euclid, if you have the photometric survey in Euclid, you can get of order 10 billions of objects, while if you go to a spectroscopic survey, you have of order of 10 or 30 million objects. So it's clear that if you do photometry, which is a faster way to get a rough estimate of your redshifts, you can get an order of magnitude more objects in order to do this kind of analysis. So this is very nice when it comes to overcoming the shot noise that you have. And basically, broadband photometry is going to take these strong spectral features and guessing what is the redshift of this objects instead of putting this thing through a spectrograph and getting a very precise measurement of the redshift. So when you do that, one thing that you have is that you have large uncertainties on your redshift. And here I'm showing the redshift distribution of sources. In black is what you would have from a spectroscopic survey, where you know that a galaxy at redshift of 1 is exactly a redshift of 1. However, if you're doing this with photometric redshift, you have an uncertainty associated with this galaxy, meaning that a galaxy which is a redshift of 1 can actually have a certain, it can be, plus or minus something which is non-negligible. So you have a large error in your redshifts, which I'm parameterizing by this parameter sigma z. So the larger this value, the more uncertain your redshift is. And if you miss this radial information, so if you are blurring the galaxies along the radial direction, the presence of these photometric errors is acting as a sort of redshift space distortion, because you don't know exactly where you're placing the galaxies, so you're blurring things along the radial direction. And when we don't have this kind of information, we usually project the galaxy field, the three-dimensional field, with this selection function along the radial direction, and when we work in the tomographic beams that surveys like DES do. So this is, there is a problem here that, so we are talking about these photometric redshifts that will have this dumping along the radial direction. And this dumping, I'm modeling here as an exponential, as a Gaussian dumping. This will remove the very large K parallels. So you're losing information from your small scales when you have these photometric uncertainties. And this is because you don't know how to place the galaxies along your radial direction. So this is the accessible modes in Fourier space. It's in the pink region by the broadband kind of photometric surveys. And this, if we want to actually recover this distribution, if you want to know what will be the redshift distribution of the sources, we can try calibrating this sample that we have, this photometric sample, with some sample that we know the redshift. So for example, a spectroscopic survey. However, when it comes to cross-correlating galaxies from a photometric survey with spectroscopic surveys, we have a geographic non-overlap. So they sample different regions of the sky. So we can use actually intensity mapping to do that, because there is an overlap between photometric surveys and 21 centimeter intensity mapping surveys. But the problem with intensity mapping, I'm not going to go into the details because this is very technical, but you can ask me later, is that the foregrounds that you have to remove from the intensity mapping in order to do cosmology with is going to dump all the very large scale modes, because this is where you have the degeneracy between your cosmological signal and your foregrounds. So you don't know how to model these, and these scales are usually dumped, or you simply remove them from your problem. So if you think about cross-correlating galaxies with intensity mapping, you see that the overlapping region here that you would have in Fourier space to do this cross-correlation is very limited. So all this red region here is not accessible by the intensity mapping. And the pink region, so the only remaining region is this where the pink overlaps the green. So it's a very constrained space that you have to do these cross correlations. So in order to proceed, we decided to use the bispectrum. I'm just going to briefly remind you what it is. So as the two-point correlation function, you measured how 2 points correlate in space. With the bispectrum, we're going to look at triplets of galaxies instead of 2 galaxies only. And here, for example, we're going to look at the excess probability of finding these kind of triangles. We could also look at these collinear shapes here. So basically, when you look at the bispectrum, what you're seeing is that you have a high probability of finding things that are in these two when they are collinear, or when they are, on the other direction. So when you open completely this triangle or you close it completely. So this you have the higher probability, and meaning that you are looking at filaments and these structures. So this is an example of how the information of the bispectrum. And the bispectrum will appear due to the very nonlinear structures that we form in the universe due to gravitational evolution. So if you only have a Gaussian initial field and you have no nonlinear physics, then you wouldn't have a significant signal for the bispectrum. So it is basically telling us how different modes will couple in the large-scale structure. So it's just to show how we can model the bispectrum. The power spectrum, the cross-power spectrum between 2 different tracers will have some certain kernel here that carries the bias of these different tracers. And you have the shot noise that will appear, which would be 1 over the number density. For the bispectrum, we have the dependence on the power spectrum that appear here, these combinations, and you also have the intrinsic power bispectrum of, if you have some non-Gaussian initial conditions, for example. And these will carry dependencies on the linear bias and higher order biases that you have in your large-scale structure. So what we try to do is basically to reconstruct the modes that we lost due to foregrounds in the 21 centimeter intensity mapping. So as I was mentioning, for the for the intensity mapping survey, you are losing the very large scales. So you are only retaining the very large K modes. So you only access very large K Fourier modes here. While for the galaxies, the other thing is happening. So for the galaxies in a photometric survey, you are completely losing the very small scales, meaning that you're only retaining the very small K Fourier modes. And when you look at the bispectrum, you have actually a coupling between these different scales. So if you do the cross-correlation between the galaxies, which you have access to the very long wavelength modes, you can actually try to recover this thing in the 21 centimeter survey, which you only have access to the very small scale fluctuations, because this thing is modulated by the long wavelength fluctuations, which is captured by the bispectrum. So this was the idea of cross-correlating galaxies with the 21 centimeter at the bispectrum level. And when we do that, we find that by using the bispectrum, so the dark blue region, I'm showing how you, the errors, the forecasted errors on the center, so how well you're placing your, the redshift of your galaxy, how right you're guessing which is the redshift of a photometric galaxy, and on the width of that distribution. So we can actually recover those, that selection function that I showed. And, sorry. And here what I'm showing is the constraints obtained with the bispectrum, or just by doing the cross-correlation between galaxies and intensity mapping at the power spectrum level. So as you can see, as we go along in redshift, for the bispectrum, you are very well, it is a very well-behaved curve, and it is completely under the Y10 requirements that you have for these two parameters of your redshift distribution for the LSST survey. While for the power spectrum, depending on the errors that you have on the photometric redshift, your constraints are completely lost if you try to do this thing with the power spectrum only. So the take-home message of this work is that using the bispectrum, if you're trying to combine galaxies and intensity mapping to recover your photometric parameters, is highly recommended because with the bispectrum you can recover those modes that are in principle lost to foregrounds. So this is just a summary of the things that I did in my PhD. From the relativistic effects kind of analysis, we saw that a dipole signal appear when you start to include relativistic corrections in your power spectrum. We developed the pipeline model, estimated and interpreted the dipolar modulation that we have by these relativistic effects in the three-dimensional clustering of halos obtained from the fully non-relativistic simulation. We neglected the integrated effects in this analysis, and no dipole detection could be claimed with our simulations. From the clustering redshift point of view, how we can use gravity to help us constraining parameters and improving the photometric redshifts, we employed the multiple tracers technique to combine the photo-Z galaxies with intensity mapping. We use the bispectrum because with the bispectrum we can have this mode coupling, and we can recover the nonlinear, we can recover the large radial scales that we 21 centimeter intensity mapping apparently lost to foregrounds. And the bispectrum is capable of calibrating your redshift distribution in situations where the two-point function is not. So I'll leave it with the conclusions. Thank you for your attention.
So you compare with G-evolution simulations, right? Because you need relativistic effects and everything. Is it possible to paint relativistic effect on top of n-body simulation, Newtonian simulations?
Yes, it is. So if you have access, for example, let me go back to the expression. So the whole idea is to mimic these effects. So if you have access to your, if you pick any-body simulation, a Newtonian one, if you have the velocity field, you can put your dark matter particles or halos in redshift space just by doing this transformation here, right? The standard transformation in your redshift. If you have access on top of that to the gravitational potential, you can include the effect of the gravitational potential in your any-body simulations, and then you would be mimicking this particular piece of the distortions. So in principle, if you have access to these quantities, you can do whatever you like, even if it is a Newtonian one. The only thing is that you would be putting by hand and you would be extracting the same effect, but yes, in principle you can do that.
Any other question?
As Actually, I have an announcement if there are no further questions. Okay, conference announcement. Tomorrow, seminar by Ellen has been cancelled because she's not well. So Archie's you talk at 11, okay? Yeah. And this is specifically very good because tonight at 7 we have the dinner, and who knows after the dinner. At 7 at Bovinus, you have the map.
Okay, let's thanks all the speakers again.
Well, we can send them by regular mail.
I guess,
no, this is Carlos. This is here.
Oh, yeah, Carlos.